slideshow. Okay. ¿Mm? Bueno, el día de hoy tenemos el gusto de que esté con nosotros el doctor Samir Aguadi. Él es de la Universidad del Norte de Texas. Me dijo que no dé detalles de su currículum, él lo dice. Y la plática que nos va a impartir es Materials for Aerospace Extreme Environment. Muchas gracias, señor Martín, por la invitación. Es mi honor de estar aquí, pero mi presentación es en inglés. ¿Está bien? Thank you so much for the organizers for inviting me to give this talk today. So my talk will be on materials for aerospace extreme environments. I'm from the University of North Texas. So the first part of my talk is very similar to the talk that I gave last year. And then the second part is very different. So I'm from the University of North Texas. I've been there since 2013. We're in the Dallas-Fort Worth Metroplex, and we are the north of Dallas and Fort Worth. So we're located in Denton area. We have about 46,000 students, and we're located in Denton, which has a population of about 160,000 people. Okay, so today, the goal of the work that I've been doing for the last 15, 20 years is to develop and critically evaluate protective materials for aerospace applications to improve their longevity, performance, and safety. And I've worked primarily in two areas, actually a little more than that, but the two areas that I'm going to be talking about today are tribological coatings, so that's to reduce friction and wear, and thermal protective systems, which are for enhancing ablation resistance of ceramic materials, basically. So for the tribological coatings, my talk will be divided into two groups. One, high temperature tribology, that's for bearings, external moving assemblies, and then in fuel pumps. And then the other one is components in high-speed aircraft and spacecraft re-entering the atmosphere. Okay, so high temperature tribology, we're trying to reduce friction and wear at high temperature. That would work for, that would be for bearings in combustion chamber, where these temperatures are around 200 degrees Celsius to 600 degrees Celsius, depending on where you are in the engine. For also external moving assemblies in hypersonic vehicles, where these are subjected to temperatures in excess of 1,000 degrees Celsius. And finally, the last project that I had on tribology is on drones. And so we worked on cylinder liners and fuel pumps in hybrid drones, where for the first generation, basically for these drones, the engine is very similar to the engine of a car. So it's not a combustion engine like an airplane. And so you have a piston, you have friction and wear and thermal protection, but they're made of aluminum alloys. And the temperatures for the first generation hybrid drones is around 350 degrees internally. And then the next generation is going to be around 500 degrees Celsius or so. Okay, so the solutions are solid lubricants or composite coatings to reduce friction and wear. Solid lubricants, you go to the hardware store, you can buy molybdenum disulfide or graphite, and these molybdenum disulfide would work in low temperature, low humidity environments. And and graphite would work in low temperature, high humidity environments. Or you create what's called the chameleon coating, which my colleague Andrei Vovodin worked on for 25 years or more. I worked on him a little bit as well on these. And that's basically creating a composite that has a hard phase for load bearing and multiple solid lubricants because each solid lubricant works well in one environment but doesn't work well in a different environment. So this would allow adaptability of these coatings so that they can work in multiple environments. So this is the composite in tribology. Andre had showed this so many times in the past, where the material surface is like a chameleon, and that's why he called it chameleon coatings. That surface changes depending on the environment you're in. For example, you have this orange surface, which represent a certain phase when you're in humid air, low temperature. And then when you go to high temperature, it's a different phase that's on your surface that lubricates. And then when you go back to low temperature, but in a dry environment, it's a third phase that helps. Okay, so the work that I've done 15 years ago was focused on ternary oxides. Why? The reason why is I looked at these materials, and the reason they're good solid lubricants is because they shear easily. They have van der Waals type of bond between the basal planes. So when you apply a load, they can shear and provide low friction coefficients. In these oxides, some of them have these layered structures. And most of the oxide I worked on are silver tantalum oxide, are silver based. So I worked a little bit on copper based, and then Poncho now has worked a lot on copper based materials more recently. And I'm not presenting his work. So the silver doesn't have good bonds to oxygen. And if you look at silver molybdate, for example, this one here, in blue is silver, in red is oxygen, and in green is molybdenum. And so you have this layered structure with, at high temperature, you can shear easily because you have a weak bond there as well. Next, so most of the work I'm going to present here is silver tantalum oxide, which I've published about 8 papers on this system because that's the system that I like the most in terms of performance and understanding and things like this. So we made silver tantalum oxide by sputtering using silver and tantalum targets and in oxygen and argon environments. The coatings had about the thickness of 2 microns, and we used for tribo testing silicon nitride ball at up to 750 degrees Celsius. So I have here 4 typical samples. The first one is tantalum oxide, which is my reference because I didn't have any power to silver. And then I increased the silver content to 25 watts, and I was able to form silver tantalum oxide single phase, okay? And you see here how the friction coefficient for the 4 different samples changed. So the first observation is your friction coefficient is going to decrease as the temperature goes up for all of them because the material is becoming a little softer at higher temperature. 2, the best friction coefficient was for S4, which is this phase, as we expected. And we had here at 700 or 750 degrees, I forgot, a very low friction coefficient of 0.04 or 0.06, depending on the load that you use. So if we use a load that's slightly higher, it was a little higher, but if we lose, or I forgot, yeah. And if the load was 1 gigapascal or like something like this, it was lower. But it was in that range. So a colleague of mine, Ashley Martini from the University of California, Merced, did simulations of where she had a rigid plate here that moves at a constant speed, and the material is at high temperature. So you can test it at from 25 degrees Celsius to 750 degrees Celsius. I mean, in simulation, using molecular dynamic simulations. So these are the important results of my 8 papers. On the left-hand side, the friction force for both simulation, which is in black, and the experiments follow the same trend. They're not the same values because we're not using the same testing conditions, and we cannot use the same testing condition in molecular dynamics as a real ball on disk test when you do wear testing. But what's more important is on the right-hand side here. I'm showing you a cross-sectional view of the wear track. Remember, the wear track had a thickness of 2 microns. Now we have a thickness from here to there. That's your coating, or what's left of the coating, and below it is the substrate. We have about 500 nanometers left, so 25% of the coating is left. And that coating is made of 2 regions now. Far from the surface, we have the silver tantalum oxide, but near the surface, we have a sort of a composite. So that silver tantalum oxide broke up into silver and tantalum oxide. And so we believe that the lubricious nature of silver tantalum oxide was enabled by the joint contributions of the hard tantalum oxide phase and the lubricious silver clusters in the shear and temperature-induced surface layer. Now, problem. Sometimes it's good to have a hard phase, not just the solid lubricant, because the solid lubricant is soft and gets worn out quickly. So we don't look at just friction, we also look at wear. I like reducing wear even more. That's more important. So what we thought of is, what about creating tantalum nitride silver or tantalum oxide silver on Inconel substrate? And then what happens when you increase the temperature? Silver is very mobile, so you have this composite. Silver is very mobile and goes to the surface and forms silver tantalum tantalate. This is not a very good picture. I should have changed it. When silver is mobile, you're going to also create defects that are left behind and porosity and all that kind of stuff. But this is also, how to say, a very metastable system. So you have to study how that, how that works. But anyways, as you can see, the friction coefficient decreased from like at 750 degrees Celsius from here down to below 0.2, which is very good. So that's still a lubricious material. And what's more important is this material had a lower wear rate than the silver tantalum oxide by itself by quite a bit, by a factor of 30 or something like this. So it was really good, or more probably. I forgot the numbers. But anyway, so now still in I'm going to talk about in situ Raman. So Andre and I built this in situ Raman before at when he was working at the Air Force. And now we have it since he joined my university in 2015. We have the same system at UNT, and actually it's in my lab. And so with the in situ Raman, basically, you have your wear tester, and you have here your friction contact, so that's your ball. And here you have a laser sampling area where you're able to measure like the Raman signal from your sample in real time, okay? And at high temperature, because this is housed in you have a furnace there, so you can do these tests up to 700 degrees Celsius, okay? So then what happens, so this is what it looks like. This is in my lab. And what I wanted to do is I wanted to study at that time vanadium nitride silver, okay? So why vanadium nitride silver? Because I was hoping that I have the same thing on the surface. So I have here a hard phase with silver, which is soft. And then silver is mobile, goes up to the surface, and is going to form silver vanadate. And I hypothesized that silver vanadate was going to be lubricious. The problem with silver vanadate, you have 2 phases of silver vanadate. You have Ag3VO4 that has that layered structure, and I expect it to be lubricious. And I have AgVO3 that is not layered, and I expect it to have a higher friction coefficient. So then what we did is we took our Raman with the high temperature, and then we looked at different regions. So here, what I'm doing is we're looking at sample temperature and time. Here, we're taking the sample. We're not doing wear testing. We just heat it. We heat it all the way up to here, up to 700 degrees. Where you see the green dot, I start the wear test at 700 degrees Celsius. Where you see the red dot, I stop the wear test. and then I let it cool down. And then I do look at the Raman each time in each region. So A, B, C, D, E. This is A, nothing really interesting. I have a nitride. I haven't started forming oxides up to 300 degrees Celsius. At about 375 and above, I start forming some of these oxides. So you see silver vanadate, a little bit of vanadium oxide as well. But it's really hard because at higher temperature, your Raman signal is going to be very weak. It's not like at low temperatures, right? So then we reach 700 degrees. I haven't started the test. Now I see both peaks. I have both silver vanadates in there. Then I start the wear test at 700 degrees. And what happens is I only see the Ag3VO4. Why? Because the other one gets removed, what gets worn out, and you only end up having on the surface the lubricious one, just like the picture I showed you before about the chameleon coatings, with the chameleon changing the skin and becoming red or green or whatever, right? And then what happens next is as soon as you stop the test, I should have a red dot here, and cool it down, and it's cooling, so the peaks get stronger. The AgVO3 shows up. So when you cool it, on the surface, you have both of them, right? So now the conclusion is the formation of AgVO3 is suppressed by the wear process. So in the wear track, I only have Ag3VO4, the good one. And during cooling, the intensity of both of them increased significantly, and we're forming the second phase of vanadate. But where this is really cool, the conclusion is, if somebody doesn't have in situ wear test and you do the test post-mortem, so afterwards, after it cools down, everybody would think I have both of these on the surface. Whereas in real time, I only have this one on the surface. Okay, all right. Next, so for the drones now, we've done also some, so the drones, or for the engine of the drone, it's made of aluminum alloy, aluminum silicon primarily, alloys. And these aluminum alloys cannot handle 300 degrees or 350 at all. So what you need to do is you need to create a thermal barrier coating on the surface so that if here you have 350, here you have 250 or less. So you have to have a thick oxide layer. Two, we also want to reduce friction because you have a piston that goes back and forth. And so what we did is instead of having a thermal barrier coating like YSD and having it as a coating, why not just create aluminum oxide out of the aluminum alloy itself by plasma electrolytic oxidation? So our friend from the University of Manchester in England, Alexei, made these porous oxide layers that are thick, that are a couple of hundred microns in thickness, and they were porous, and they were able to provide that thermal protection. Now, the porosity is also a good thing because porous materials are going to provide lower thermal conductivity. And I also can put stuff in that porosity to reduce friction. So I can put small powders into that porous area and create a chameleon coating again, which is that composite that I was talking about at the beginning of my talk. And that is done. So it's easy. You just burnish these powders that are mixed, that you mix them, and then you burnish them into these pores. And we got some really good results with this. So you can see here, on the left-hand side, if we didn't have the burnished coating, so the coefficient of friction is super high. And then as soon as we burnished, look at, especially at 300 degrees, which is the temperature at which these operate for the first generation materials. So this is, look at beautiful, almost 0.02 friction coefficient, which is really amazing. Now, I don't have funding in this anymore. But the next generation that our colleagues might work on is we need to go to 500. This is not going to work at 500 with MOS2. we would probably replace one of the phases with boron nitride, maybe, and try that. And I think that will probably work. Okay. Anyways, next, this is the part I didn't prepare as much. So we have also in the drones, what we got funded, and it just ended, is scuffing issues in low viscosity fuels. Again, this is for drones. These drones can be military or non-military, because the drones they're building a lot of them for for commercial use. Like Amazon and Walmart now is bringing things to your house in a drone. Then drones have to be hybrid, because to have a higher load, electric ones are not going to do the job. And of course, for military applications as well. So scuffing is the sudden failure of lubricated components under extreme conditions of load and speed. All of a sudden, like, and before these were for like Department of Defense, they had just stainless steel for these pumps, like for the fuel pumps, and they failed dramatically because of scuffing. So the causes are increase in surface roughness, formation of an oxide layer, and then all of a sudden, if you do like a wear test and you do scuffing test, the friction was like this, let's say 0.2 or whatever, and all of a sudden it spikes and it becomes super high and it starts seizing. So the leading theories for initiation of scuffing are poor fuel lubricity, an inconsistent quality in the field, inability of fuels to resist scuffing during momentary loss, because sometimes you have momentary loss in these fuel pumps, and then debris in the pressure regulator as well. They can also help with the scuffing. So some companies started using ceramic coatings, like DLC and others. They haven't worked. So the Department of Defense asked us to do this project. And initially, this project was not sciencey at all. I was a little bored. So what we did is we tested 30 materials, and we tested them in different fuels. So the fuels were decane, dodecane, ethanol, and F-24 jet fuel. And the reason why is for the Department of Defense, they wanted to have a drone where you can pour anything you want in it and it should work, whether you use this or this or this or this. So it's a multi-fuel capability. You cannot just use one fuel because it depends on where you are. Okay? So we tested 30 materials and we created these design maps or like Ashby type plots. I'm not showing you all 30 materials because then it would be so busy, the pictures. This shows you two figures, one with average coefficient of friction as a function of average flat wear, and the other one is average counterbody wear as a function of average flat wear. And the counterbodies we used are alumina that represent an inert environment, and steel. And these are the tribology test conditions. Now, if you think, for example, a nitride, they're going to be in the same regions. If you think of a coating that's a titanium nitride, titanium aluminum nitride, they're all going to be the same. So we looked at different families of coatings. Now, in addition to different families of coatings, we looked at PVD and thermal spray as well. Okay? All right. So where we want to be in these are down here. So local, and especially down here. You see these tungsten carbide, cobalt, chrome are fantastic. The chrome nitride is close. It's also good. And so we decided to do the next step. And the next step is to do cylinder on flat tests. And we selected these materials where you have the cylinder is coated with something and the flat is coated with something else, or they were coated, with the same material. And some of them were not coated at all. For example, here we had steel. One counterface is a steel and the other one is a chrome nitride. Now, again, this was a project that was primarily not sciencey, so we were just like generating a lot of data. And what we found was We also generated these Ashby type plots in decane, dodecane, ethanol, jet fuel. And we found that these three systems, including chrome nitride, were the best ones in these low viscosity fuels. So tungsten carbide cobalt, tungsten carbide cobalt chrome. You know who makes these? Satish Dixit from California. Their company makes them. And this one, I think, are made by Woodward in Colorado, the coatings. So we got these coatings. We didn't make them. We bought these coatings commercially because they wanted to have a solution really fast. Now, in addition to having a solution fast, they also wanted us to look at, are there any other materials that do not exist in industry that we can also create or develop? So what we did, so I'm going to go over these really quickly because we just started publishing them. And one of them is really cool. We can do materials and surface modification by creating these, just by spraying. By spraying these molybdenum disulfide. I was like, what about molybdenum disulfide? Can it work? So you see here some of the data. In dry, ethanol, dodecane, coefficient of friction, or like the steel counterbody wear rates. And you see that ethanol is always a problem. Ethanol is very corrosive. So even for your cars, so like we have like 10% ethanol when we put like when we buy gas. Ethanol is a harder is harder on the wear and all that kind of stuff. So but what you see here is three systems: molybdenum disulfide alone on steel, and then the really good carbide. And then you can also do a solid lubricant on top of a hard carbide. And those were better. If you have two coating system, that behaved better because you have a lubricant and you also have a hard phase underneath it for load support. Two new systems that we created, and I'm going to go over these quickly, see how much time I have, is the tribocatalytic systems. And tribocatalytic system is making a nitride and adding copper particles in it. Why? We had this idea from the work done by Ali Erdemir, where Ali Erdemir used similar systems with copper, where copper is a tribocatalytic system in oils. And in oil, the copper helps break up the oil into carbon, and that carbon forms on the surface and lowers your friction coefficient. So because our fuels also have carbon in them, we thought the same thing would happen, and that's exactly what happened. So we have here, significant reduction in friction and wear by having copper incorporated in these nitrides. That's one. Correlation between carbon and copper in TEM. So wherever we see copper in TEM, we see carbon on top of it. And wherever there is no copper, we don't see carbon. So there is a correlation. So the tribocatalysis can protect seals from scuffing via in situ generation of lubricious carbon films. The last one I'm going to talk about is the problem is what I said here or earlier. The ethanol is a problem. What we found, and we haven't published it yet, so I cannot talk too much about it yet until it gets approved, is we did graphene in MOS2, and these graphene reoriented and helped. The problem with MOS2, it oxidizes in ethanol. And having graphene in there reduced that oxidation of MOS2. And so in addition to reorienting and providing even better friction coefficient, it also prevented MOS2 from oxidizing. Like I said, this, I'm not going to talk about it too much, but this is a schematic that shows you the mechanism of how that helped. All right. The last part of my talk now is not tribology, it's high temperature ceramics for, let's say, reentry or for hypersonic travel, hypersonic vehicles that are traveling. NASA has worked on this for a long time for reentry, but they didn't use ultra high temperature ceramics. They used carbon-carbon fibers. Carbon-carbon fibers work well for a short time. So the carbon-carbon fiber, when the shuttle comes back, it comes back and then it starts like decreasing its velocity, and so the surface is going to be hot for a few minutes, maybe at most, like maybe 2, 3, 4 minutes, and then it starts to reduce, like the temperature decreases. Hypersonic vehicles, you go from here, let's say, to Australia, you're going at super high speed for a long time at high altitude, so you have lower oxygen partial pressure, but it's still, you have oxygen, and carbon-carbon fiber don't work. So one of the things I looked at is thermal protection with the lead material is hafnium carbide, silicon carbide system, but it has problems. So why hafnium carbide based? Hafnium carbide has the highest melting temperature of any material. It's close to 4,000 degrees Celsius. That makes it hard because these materials are usually sintered. You make powders of hafnium carbide, silicon carbide, you mix them, ball milling and all that kind of stuff. And then you sinter them. And when you sinter, you have to go to 2/3 the temperature of the melting temperature of your material. So 2/3 would be close to 3,000 degrees Celsius. So we add silicon carbide but it still have a problem. Why? Silicon carbide above 1,600, these materials are like gonna reaching 2,400, 2,500 degrees Celsius during when the hypersonic vehicle is going really fast. At 1,600 degrees or above, silicon carbide turns into silicon oxide, and that silicon oxide evaporates and escapes and forms a porous material underneath it. So I want to reduce that silicon escaping from the surface. How do I want to do that? By adding a third phase, tantalum carbide. I assume or hypothesize that tantalum carbide will help reduce the active oxidation of silicon carbide that leaves, creates a glassy silicate phase that facilitates self-healing of pores and cracks. So I hypothesize that I'm going to make a glassy material, and we will reduce oxygen diffusion by having a very dense layer on the surface instead of a porous layer like I would have here. Here I have a very porous layer, then oxygen just keeps on diffusing in. And then these materials like break really quickly. So how do you make these? So I'm not doing coatings. Maybe one day I'll do coatings and or 3D printing, which I haven't been done either. And I generated these so that you know by ChatGPT. So the first one is pressureless sintering. So you take hafnium carbide, silicon carbide, you press them, and then you put them in a furnace and you sinter. This is hard because you don't have extra energy. Hot pressing, I have hot press as well. We press, put them in a hot press, and you apply a lot of pressure to make it denser, and that allows you to go lower in temperature than this one. Okay, this one usually people go to 2,300 degrees Celsius to sinter them properly. This one you can go 2,000 or 2,100. And then there is also spark plasma sintering, which my colleague has, I don't have, is you also apply ultra high voltage, and it creates a mini plasma sparks between the powders that you compress. And that also allows you to go to lower temperatures and have a denser material. I personally like this one more. Most people like these two. Why? With this one, if you can go to lower temperature, you can make any shape you want. The spark plasma sintering can only be done in small samples and flat samples. Hot pressing you can do bigger, but they're still flat samples. And then these are, you can make anything. You can do 3D printing if you want, and then you sinter it, and you can have any shape you want. And that's more important because for these to work, and you're using the leading edge of your hypersonic vehicle, you can also vary the shape. You can have it like a cone shape, not flat necessarily if you want to. So you can make any shape depending on what you're looking at. So this is what our system is. So now I'm focusing mostly on pressureless sintering. We did our work at 2100 degrees Celsius. So we heat the furnace and we keep 2100 Celsius for an hour. And then we made our samples. So these are the samples we made. 0% tantalum carbide, 5, 10, 15, 20. And from here, what you see is the relative density increased. So tantalum carbide helped have at 2100 degrees Celsius, 98%. The hardness of the material also increased. At that time, yeah. Flexural strength also has increased. So you know flexural strength. You have ceramic material. You have two things here, and then you apply stress on the top until it breaks. So you look at the flexural strength. And you look at the reduction in the carbide thickness. And the way you do that is you do an ablation test. An ablation test is basically having an oxyacetylene torch close to the sample. So you see here our samples. This is done at an army base. And you go and heat it, and with the oxyacetylene torch at 24 or 2500 degrees Celsius. And you do it for 1 minute, 5 minutes, 10 minutes to 25 minutes and stuff like this. So for this first paper that I can present, 10 minutes for all. I'm working on a second paper that I cannot present yet. We did it tests at 25 minutes. That was most of the material that they tested, all broke at 25 minutes like this. Mine did not break, so we just did the patent on this system. So it was really good. The second thing that I was going to mention, which is not here, is recently my student was trying to make these samples, and the machine stopped. So he reached 1800 degrees Celsius, and then I don't know what happened, stopped and went down. The temperature went down, so we didn't really sinter. He took the sample, and it was as good as these at 1800. And I've never seen anybody sinter these at 1800 degrees Celsius. So this is really, 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 really cool. So the addition of tantalum carbide has been fantastic. These are pictures of SEM and EDS of all the samples as a function of tantalum carbide. All I want you to know is I see more silicon with tantalum carbide. So the silicon carbide, silicon is not escaping. So you have your oxide layer on the surface, and then you have the carbide underneath it. So this is your oxide layer. This is your carbide. And silicon here has escaped mostly. The other ones have not escaped as much. Maybe a little bit on the surface, and you still have a little bit of porosity, but it's way better than not having tantalum carbide. Okay? And I'll explain why that's the case. We did, maybe how much time do I have? I have 20 minutes? Okay. So basically here, this is Raman. The Raman data also shows what phases we are forming. And this is without tantalum carbide. I only have hafnium oxide mostly. I don't even see silicon oxide. Here I see silicon oxide, which is the red. You know, here I see barely here, but here I see a lot more of silicon oxide. You can see from Raman system. This is a cross section. So this is your oxide layer, and here you have your carbide that hasn't oxidized yet. Okay. All right, next. Now this is really the cool thing. This is a cross section of my oxide layer on the surface. And what it shows is I have here hafnium oxide or hafnium tantalum oxide. That's the hard phase that can crack and break and blah, blah, blah. And I have here, and also in the cracks, this phase with these circles. And that phase is, I think, the glassy phase, which is viscous, that self-heals all your, like, the entire material. So that glassy phase forms and goes wherever there is a crack or a porosity or that's left behind or something, and keeps the material together. I think these cracks formed after cooling down and or because of the, we're gonna do TEM on them. I think, again, I don't know. So I don't know where they came from. But this is the cool stuff. So we looked at different regions of that oxide layer, and especially in that glassy phase. And that glassy phase has these circles, and the circles are tantalum and carbon rich. So they're tantalum carbides. And the other the other region is amorphous, but that amorphous region looks like it's made of two amorphous phases that are interlaced. One is, as you can see here, one is silicon rich, and the other one is hafnium rich. And so the TEM EDS mapping suggested that this amorphous matrix was comprised of two interwoven regions, one enriched in hafnium and the other one in silicon. Next, then we started zooming in. There's two regions, one in the middle of the oxide layer and one at the bottom of the oxide layer near the carbide layer, just to see what's going on. And so what we found is here I have cubic tantalum carbide from the diffraction patterns in that amorphous phase that's viscous. And here, near, as you get closer to the surface, the tantalum carbide turns into Ta2C. And then near the surface, there's no Ta2C. It becomes tantalum oxide, right? And so this is really, really cool that that shows you what that phase does in the different regions and in different oxygen partial pressures. I did, and I'm not an expert at this, volatility diagrams at these high temperatures. And we found that, yes, depending on the partial pressure of oxygen, so we did these simulations with FactSage, you start forming TAC, and then the TAC turns into Ta2C, and then it oxidizes when your partial pressure goes up. So deeper, we have here TAC, then Ta2C, and this is the story of what's going on depending on the partial pressure of oxygen. All right. Is everybody okay with this? Okay. Now this is, and I know this is, how to say, thermodynamics is stable phases that you get, and we're dealing with metastable stuff. But these are the two phase diagrams that I found. And what I think I'm getting is that two interlaced regions consist of an interwoven matrix of hafnium silicate and hafnium tantalate. Hafnium silicate is going to be more, silicates are viscous at high temperature. That's a known fact. And this hafnium tantalate is amorphous region, is also viscous, but not as viscous as this one. So now the new studies I'm doing is like I'm trying to make these and trying to understand them, understand their viscosity, and understand how they affect these materials, etc. So the conclusion of this part is mechanical properties. So the hardness, so the addition of tantalum carbide has been fantastic. I'm planning, and I published one paper on this, well, this week. The other three papers we're working on them. But we've gotten some amazing results. So the mechanical properties are better. The porosity of hafnium, we don't have porosity like we did without tantalum carbide. And we believe that tantalum carbide dissolves to form Ta2C, tantalum 2 carbide, embedded within hafnium silicate and hafnium tantalate, which are your viscous regions that are self-healing to your material. And then the tantalum 2 carbide nanoparticle underwent also oxidation near the surface, so you don't see that anymore. And the tantalum oxide contributed to the continuous supply of tantalum to the evolving glassy phase, which is a good thing. I think I'm not going to talk about this. So this is a new system. We received it. I mentioned it, I think, last year. So this is a new system that we have a new lab constructed. We're going to have a big opening at the end of November. where we have samples that we can test for their flexural strength in an in situ XRD system. So we have an XRD system, and that XRD system can go up to 4,000 degrees Celsius, or you can go up to 2,000 in a furnace, or 4,000 with a laser. So it's local. You cannot take a big sample and with a laser do that, but we can at least learn certain things. We have a micro XRD system where we can look at different regions of what's going on and do also mechanical testing at the same time. We can do tensile testing for alloys and all that kind of stuff. We can do compression testing. We can do flexural strength testing while we're taking XRD data at very high temperature. And that this system does not exist anywhere else. So this is really, really, we're really, really excited to have that, except for now, no more dinero in the US. So anti-science, oops. Anyways, so summary, I talked about ternary oxides are effective high temperature solid lubricants. I talked about adaptive coatings. I talked about fuel pumps and things like this. And finally, I talked about the addition of tantalum carbide that has been fantastic in providing thermal protection systems for high temperature hypersonic applications. And thank you. I gave this talk. So some of the cool stuff, and I'm not going to get into the details, is, and I'm not very good at this, maybe it's my age, big data, machine learning, and all that kind of stuff. There is so much data for different systems, and it's really hard to tell, and each person tests these things differently and all that kind of stuff. So it's really, would be really nice to start doing some big data machine learning and maybe start with our system. Why? And I started asking ChatGPT, but I don't trust it. Like what do you expect to happen with hafnium carbide, silicon carbide, tantalum carbide? We're the only ones that do that, so we can create new data. There's other people that have done hafnium carbide, silicon carbide, so I can use that also as a data, or hafnium carbide, tantalum carbide alone, but binary phase. So can we, with all of this, predict what could happen with these properties at so there is a lot of stuff that can be done, especially that we have a lot of data, but other systems have also a lot of data in them. So anyways, for the high temperature ceramics especially, and even for tribology, actually for the other work where we did the Ashby plots and all that kind of stuff. So this was acknowledged funding from the Army Research Lab and Air Force Office of Scientific Research, my collaborators from UNT, from Army Research Lab and UC Merced, and then finally students that have worked on these projects over the years. Thank you so much. Muchas gracias. Si tú quieres preguntarme en español, está bien.
Muchas gracias al doctor Samir por su
Gracias.
interesante plática. Ahora es tenemos tiempo para preguntas. ¿Alguien tiene alguna? ¿Son questions?
He has a lot of questions. I know this guy. Pancho.
En la diapositiva número 19 acerca de las mediciones de Raman. Está haciendo la medición.
Yeah.
Es que creo que perdí algo. Cuando está,
está
girando la muestra.
¿Este o la otra? Oh, which one? Oh, 19.
19.
I don't see the numbers. Oh, este.
Ajá.
Okay.
¿Cómo son las mediciones? Y, por ejemplo, dice, durante el enfriamiento, la intensidad del vanadato incrementa significativamente, pero el enfriamiento es gradual o lo están enfriando de una manera diferente o rápida.
Yeah. Okay. Your sample is like this. your ball is here that measures the friction. Your laser is here. So it's not, but the other one is going fast. So it's like 60 turns per minute or something like that. So it's continuous. The only thing is we also did outside of the wear track, and we found the two phases, and inside of the wear track, I only see one phase. You see what I'm saying? So we checked both of them. Outside, both always. Inside, the other one was removed. Does that? Okay. Thanks.
¿Alguna otra?
Pancho.
Oxidation of the hafnium carbide. That's a little bit lower than the melting temperature.
Yes.
And you have
It's
oxidation of the
that melting temperature for hafnium oxide is like I think 2750 or something, or 3000. I forgot.
Yeah, in oxidation, I think it's like 1700 based on ChatGPT. But
This guy.
but is that an issue for this applications for the supersonics?
Well, everything is going to oxidize at these high temperatures. And hafnium, I mean, I've picked hafnium oxide as the best material. Again, I'm not saying most people that work on this either pick hafnium carbide, zirconium carbide, hafnium diboride, zirconium diboride. That's it. Those are the four. Because they have the highest melting temperature. Zirconium would be cheaper. I'm going to try zirconium to do 3D printing. Because it's very expensive, hafnium carbide. And only 2 countries have it. You have to buy it. China, Russia.
Thank you for your talk. Following up on that question, what would be, is there a passivation thickness in terms of the oxidation, the maximum oxidation thickness that you would have? Or, I mean, if you have a larger time, heating time, that layer will increase?
That's a good question. And to be honest with you, I haven't studied that. Submitted some proposals. I'm probably not going to get funded now. But with the high temperature XRD, we want to do these studies, but that's oxidation only. So in oxygen, you're heating it and oxidating. Oxyacetylene is a little closer to the real application of hypersonics. It's better than oxidation alone. So the mechanisms are different. I want to see if we can correlate these mechanisms, and I don't know if they're correlatable or not. Do you know what I'm saying? So with the other one, you have like a lower partial pressure of oxygen. So that all that stuff is a realm by itself to be investigated. Yeah. Yes. Yeah. Yes. Agreed. And that's where I'm also like, I'm more of a coatings person. So I'm like, how do I use this for a coating? Well, it has to be thermal spray or even thicker coatings. Is it possible, or is it by 3D printing? I mean, like, so there's a lot of things. Yeah. Yeah, I agree 100%. And that's something that we're planning on studying. Now, the studies that we're doing is how does silicon carbide also affect things? We are having too much silicon carbide compared to what other people do. If we reduce it, is it going to be better or not? Like with that silicate self-healing. And then I'm also looking at what happens with time. So one of my students is working on one, and the other one is like, what happens to the oxide layer when I do how to say, torch test for a minute, 5 minutes, 10 minutes, 15 minutes. And then with the new system, just with oxidation. And then can we correlate them or not? I don't know the answer to that. He's loud.
I think you go.
How? Okay. You're talking which Raman? Raman for tribal. Okay, 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 okay. Yeah, yeah, this one here. Yes. Yes, true. Yes. Yeah. Yes. Yes. Yeah. Okay. Two things. One was just really cool, and I should have brought it. Is a wear test, like, but this is I haven't published yet. You see, it's like a self-lubricating material. That viscous material, you do the wear test. We had the camera the last test we did, but I can show it because I have to have approval and blah blah blah. And it goes like a self-lubricating material. Like you have all that stuff goes up to the surface and goes on the sides when you have a lot of silicon silicates, right? I agree. I don't think we know and that's why I think AI and all that kind of stuff could help. Maybe we don't have the models. The model that we have for MD, I can ask my colleagues like, hey, can you do MD 2,500 degrees? No, the force fields are not correct. It's not the same as a room temperature, or even going to a few hundred, like a few hundred degrees Celsius. So it's really hard. The thermodynamics, the same thing. It's really, and it's not just thermodynamics and kinetics. We don't understand the physics and the chemistry, and we haven't connected them. But how many people do you know that do these tests at 2,500 and some? So that's a new realm, and there's so much that can be done. Mm-hmm. Mm-hmm. Yes, predict that. Yeah, yeah, yeah. I agree. Yes, yeah. Okay. Also, this before you know me, I've worked on coatings. I'm getting a little. Um, then the guy that we started working with, the program manager, we did a little bit of thermal barrier coatings, high temperature, but I didn't get funded on that. And then all of a sudden, he's like, "Well, I'm not going to get funded on this. I'm going to get funded on high temperature ceramics." I've never worked on high temperature ceramics. This was 3-4 years ago. I don't know anything. I don't know even. I'm a physicist. I didn't even know sintering. So simple things like this that our students know better than me. I was like, what? And so I'm like, okay, I can do this. We can do this. We can do this. And we're getting some really, really good results with this. And yeah, but there's so much. We need to collect all the data. Yeah, agreed. Yes, yeah, agreed.
¿Tenemos tiempo para una pregunta, última pregunta? ¿Si alguien tiene? ¿No? Bueno, pues agradecemos al doctor Samir. Thank you. ¿Podemos pasar al coffee break?
Let's take this off. This is them telling me. You can prove that totally. No, no, my bad. Oh, yes. I'll do it.
voy a colgar aquí, porque con el pantalón luego se cae. Ujú. Sí, bien, bien. Ok. Y ok.
Los invitamos a pasar sus asientos para continuar con la siguiente sesión de presentaciones.
Creo que así está bien. Esto para atrás, sí. Ujú. Sí, y láser.
La siguiente presentación es impartida por Olinka Ramírez Soto con el título de Contracción de gotas binarias por efecto Marangoni.
Bueno, buenos días, muchas gracias por su asistencia. Mi nombre es Olinka Ramírez Soto y hoy les voy a presentar un proyecto de investigación que realicé anteriormente en el Max Planck Institute for Dynamics and Self-Organization. En este proyecto nosotros estábamos interesados en estudiar cuál es la dinámica de mojado de un líquido cuando éste presenta gradientes composicionales. Entonces, para esto lo que nosotros utilizamos como sistema modelo son gotas compuestas por mezclas binarias que al evaporarse generan un gradiente composicional en el líquido y esto induce la contracción por efecto Marangoni. Entonces, para platicarles sobre este trabajo, dividí la presentación en 4 secciones. En la primera les estaré presentando qué son las gotas contraídas por efecto Marangoni y su relevancia. Después les describiré la metodología que nosotros utilizamos y presentaré uno de nuestros resultados principales. Y por último, daré unas conclusiones generales. Entonces, el movimiento de un líquido sobre una superficie sólida es un proceso que podemos ver comúnmente en todas partes. Por ejemplo, en procesos en la naturaleza, en aplicaciones tecnológicas y en nuestra vida cotidiana. Pero, ¿por qué estudiarlo? Bueno, porque es interesante. Por ejemplo, nos da curiosidad que las gotas de lluvia adoptan diferente forma en diferentes plantas. O, por ejemplo, podemos tener diferentes texturas con diferentes pinturas sobre diferentes superficies. También los estudiamos porque son útiles, por ejemplo, para remover la lluvia de las ventanas de nuestros coches, para cuando nos secamos el cabello o cuando limpiamos los sartenes después de haber cocinado. Y una tercera razón de por qué los estudiamos es que este proceso es un proceso multiescalar. Es decir, el comportamiento macroscópico del líquido va a depender tanto de procesos moleculares como de procesos hidrodinámicos. Y en la comunidad que estudia dinámicas de mojabilidad hay un debate en el que se pregunta qué mecanismo es el que gobierna, los procesos moleculares o los procesos hidrodinámicos. Entonces a nosotros nos interesaba estudiar eso y además queríamos saber cómo es que afectan los gradientes composicionales de un líquido. Entonces para ello primero me gustaría mostrarles estos primeros 2 videos. En el primer video tenemos una superficie de vidrio que se puede caracterizar como superficie de alta energía, que es hidrofílica, ¿no? Entonces tenemos una gota de propanodiol colocada en la superficie y veamos cómo se comporta. El líquido trata de esparcirse por completo formando una capa delgada. Este comportamiento lo observamos para todos los líquidos, incluyendo el agua. Ahora veamos este segundo video. En este segundo video tenemos una superficie bastante similar a esta otra y nuestro líquido va a estar compuesto por una mezcla de propanodiol y agua. Entonces arriba vemos la gota y aquí abajo es el reflejo de la gota. Entonces a la hora de que colocamos la gota sobre la superficie, vemos que esta no se esparce por completo y por el contrario se mantiene contraída. Al frente de la gota, en la orilla, en la línea de contacto, se ve que se forma una película precursora. Y bueno, estas gotas se mantienen de esta forma contraídas por varios minutos Y el responsable de esto es un flujo Marangoni dentro de la gota, que por esto se le llama contracción por efecto Marangoni y en inglés Marangoni Contracted Drop. Entonces, este fenómeno es de interés porque podemos controlar el comportamiento del líquido si cambiamos las condiciones ambientales de humedad, ¿no? Entonces, ahora les muestro este video donde tenemos igual un líquido, una mezcla de propanodiol y agua sobre una superficie de vidrio y en un ambiente que está muy húmedo. Entonces, el líquido lo que está tratando de hacer es esparcirse por completo sobre la superficie. Pero ahora, si cambiamos el ambiente a un ambiente seco, vamos a ver que el líquido se va a contraer. También podemos controlar el desplazamiento del líquido generando un gradiente de humedad en el ambiente. Entonces, en este video, de este lado tenemos un ambiente seco y de aquel lado tenemos un ambiente húmedo. Y entonces vemos que la gota compuesta por esta mezcla se desplaza hacia la región húmeda. Este comportamiento lo vemos tanto en superficies lisas como estructuradas. Entonces, por estas razones, ha sido de interés y ha sido utilizada en la industria de semiconductores, porque estos líquidos se pueden mover fácilmente y sirven para limpiar las superficies cuando se están fabricando los chips. Ahora, ¿cuál es el origen de la contracción? Bueno, necesitamos 3 requerimientos. El primero es que los líquidos que componen la mezcla deben de ser miscibles. El segundo requerimiento es que uno de estos líquidos debe de tener una tasa de evaporación mayor que el otro. Y el tercero es que este mismo líquido debe de tener una tensión superficial también mayor que el otro líquido. Entonces, cuando nosotros colocamos el líquido sobre la superficie, la gota se empieza a evaporar por difusión de las moléculas en la interfaz libre de la gota hacia el campo lejano. Y la tasa de evaporación va a estar dada por esta relación, donde R mayúscula es el radio de la gota, R minúscula es la coordenada radial, lambda es una función del ángulo de contacto, y cuando las gotas tienen ángulos de contacto menores a 90 grados, el perfil de la tasa de evaporación va a tener esta forma que están representadas con las flechas. Es decir, no es uniforme a lo largo de la gota y es mucho mayor a las orillas a lo largo de la línea de contacto, ¿no? En comparación a lo que pasa en el centro. Entonces, esta configuración de la evaporación nos va a generar un flujo capilar. ¿Por qué? Porque se está perdiendo mayormente líquido hacia las orillas. Y entonces el líquido trata de reponer el líquido perdido con el líquido que está en el centro. Entonces se genera un flujo que va del centro de la gota hacia la línea de contacto. Al mismo tiempo, esta evaporación nos va a generar un gradiente composicional, porque los dos líquidos tienen diferentes tasas de evaporación. Y entonces, a la orilla de la gota vamos a tener una mayor concentración de líquido que se evapora menos. Y entonces esto nos genera un gradiente composicional. A su vez, como los líquidos tienen diferentes tensiones superficiales, vamos a tener un gradiente de tensión superficial que va a ir de la línea de contacto hacia el ápice de la gota. Y este gradiente de tensión superficial nos va a inducir un flujo Marangoni que es el que se va a oponer a que el líquido se esparza sobre la superficie. Entonces, en el ejemplo que les he dado de la mezcla de agua y propanodiol, el agua es el líquido que tiene mayor tasa de evaporación y mayor tensión superficial. Ahora, hay un debate de cuál es el mecanismo que mantiene contraídas a las gotas. Entonces, en este estudio, el de su derecha, presentan que la forma de la gota va a estar dada por un balance entre el flujo capilar y el flujo Marangoni. Y de este otro lado, en este otro trabajo, lo que dicen es que entre la gota y la película precursora va a haber un cambio de tensión superficial en una región muy pequeña. Y entonces la forma de la gota va a estar dada por el balance entre las dos tensiones superficiales en dirección horizontal. Entonces, ¿cuál es el mecanismo que gobierna? Porque los dos mecanismos son esencialmente diferentes. Uno está basado en un proceso hidrodinámico y el otro está basado en un proceso molecular. Entonces, a nosotros nos interesaba, pues, cómo podemos resolver esto, ¿no? Y además, en estos modelos, la distribución de la tensión superficial es diferente. En uno tenemos que el gradiente solo se representa en una región muy pequeña y el otro pues se distribuye a lo largo de la gota. Entonces, para responder estas preguntas, nosotros proponemos este siguiente aparato experimental. En este aparato experimental controlamos la humedad. Construimos una caja donde controlamos la humedad y colocamos nuestras gotas. Para controlar la humedad hacemos una mezcla de nitrógeno seco con vapor de agua y dependiendo de la mezcla es como ajustamos la humedad a diferentes valores, ¿no? Esta caja la colocamos en un microscopio que va a estar equipado por un objetivo de inmersión en agua y una cámara de alta velocidad. Esta cámara de alta velocidad nos va a servir para ver unas partículas fluorescentes que nosotros agregamos a nuestras mezclas para poder visualizar cómo es que son los flujos dentro de las gotas. Al mismo tiempo, también tenemos esta otra cámara que nos permite ver a la gota en una sección transversal y con esto podemos medir el ángulo de contacto. Entonces aquí les muestro un video de cómo se ven las gotas, cómo se ven las partículas moviéndose dentro de la gota, ¿no? Entonces este es un plano paralelo a nuestra superficie. Toda esta zona negra es fuera de la gota. Aquí donde se van acumulando estas partículas blancas, es la línea de contacto y todo lo que está acá es dentro de la gota. Y entonces lo que vemos es que las partículas se mueven del centro de la gota hacia la línea de contacto. Y cuando llegan a la línea de contacto, la dirección se invierte y las perdemos de vista porque se mueven hacia planos superiores, ¿no? Entonces obtenemos una secuencia de imágenes como estas para distintos planos y a partir de hacer un análisis utilizando la técnica Microparticle Image Velocimetry, podemos obtener el perfil de velocidades en la sección transversal. Y entonces tenemos esta gráfica que es la dirección Z y D es la distancia a la línea de contacto. La línea azul es el perfil de la gota, la interfaz libre de la gota, y estas líneas negras representan cómo es el flujo dentro de la gota, y las flechas, la magnitud de las flechas nos representa la magnitud de la velocidad, ¿no? Y entonces nosotros podemos ver que el flujo va así, es decir, tenemos como un rollo convectivo, ¿no? Y ese rollo convectivo es característico de un flujo Marangoni. A partir de estos perfiles de velocidad, podemos obtener la velocidad radial en la interfaz libre de la gota con respecto a la distancia de la línea de contacto. Y a partir de esta, podemos calcular el gradiente de tensión superficial. El gradiente de tensión superficial, con esta relación, ¿no? Entonces, aquí cumplimos una de las cosas que queríamos, ¿no? Obtener el gradiente de tensión superficial. Ahora, si graficamos ese gradiente de tensión superficial en una ecuación logarítmica, vemos que sigue una ley de potencia. Ahora, hasta ahorita les he mostrado solo la mezcla de propanodiol y agua. Nosotros utilizamos otros dioles que tienen otras otras tensiones superficiales y actividades superficiales. Pues vemos que siguen, ¿cómo se llama? Un mismo comportamiento. Y esto para nosotros era sorprendente, porque si vemos la gráfica de la tensión superficial con respecto a la concentración, esperaríamos que para un cambio pequeño de la composición tuviéramos diferencias en los gradientes de tensión superficial, y esto no es así. Entonces debe de haber otro mecanismo que es responsable de que todos estos se parezcan. ¿Y cuál es este? Pues nosotros encontramos que es la dispersión de Taylor, y que cuando la incorporamos a la ecuación de la película delgada para fluidos, recuperamos pues esta ley de potencia. Perdón, ¿todavía? Bueno, ¿qué es la dispersión de Taylor? Para describir esto me gustaría que pensáramos en esta situación. La línea amarilla que tenemos ahí, pensemos que es un líquido que está dentro de otro líquido que es el azul. Por difusión molecular, esperaríamos que esta línea presentara difusión molecular solo en la dirección horizontal. Pero ¿qué pasa si el líquido azul presenta un flujo que tiene un perfil de velocidades como este? Esa línea se va a tener que desplazar como el flujo, pues, como el flujo lo presenta. Y en este caso, vamos a tener difusión molecular, no solo en la dirección horizontal, sino también en la dirección, en la dirección vertical, ¿no? Porque tenemos un gradiente composicional también en la dirección vertical. Y entonces esto es a lo que se le conoce dispersión de Taylor. Y la dispersión de Taylor va a aumentar la difusividad efectiva. Y por lo general, se supone, para películas delgadas, no consideran que la dispersión de Taylor sea relevante. ¿Por qué? Porque por una película delgada es delgada y se piensa que la composición va a ser uniforme en la dirección vertical. Entonces nosotros decimos que no y la incluimos en la aproximación de lubricación para escribir películas delgadas. Y cuando la incorporamos vemos que pues sí es necesaria, ¿no? Para describir lo que hemos observado experimentalmente. Entonces aquí tenemos el gradiente de tensión superficial. Las líneas, estos son los experimentos a color. Las líneas negras son las simulaciones. Y tenemos cuando no tenemos dispersión y cuando hay dispersión de Taylor. Entonces ahí se ve que requerimos incluirla. Igual, si tenemos simulaciones con experimentos, perdón, simulaciones con la dispersión de Taylor, vemos que se ajustan, ¿no? También los perfiles de velocidades. Y en el caso del ángulo de contacto, pues el ángulo de contacto nos muestra cómo es el comportamiento de mojabilidad del líquido, ¿no? Entonces, medimos el ángulo de contacto con respecto al tiempo. Si no incluimos la dispersión de Taylor, no describe el comportamiento de mojabilidad. Y si le incluimos, sí lo describe, ¿no? Entonces, no sé si tengo tiempo para conclusiones. Ok. Bueno, si quieren, pues ya para preguntas, que se me fue el tiempo, pero bueno, el mensaje es que pues requerimos incluir la dispersión de Taylor para describir películas delgadas y, bueno, películas delgadas compuestas por mezclas. Y además, no es suficiente con medir el ángulo de contacto, sino que también necesitamos medir los flujos internos para determinar qué mecanismos son los que gobiernan pues la dinámica de mojado. Entonces, con eso terminaría. Muchas gracias.
¿Alguien tiene alguna pregunta?
Eh, en este caso, bueno, para propanodiol son completamente miscibles, ¿no? Y no vemos nada, nada diferente que más que los flujos internos, ¿no? Pero si utilizamos, por ejemplo, hexanodiol, para cierta concentración empezamos a tener separación de fases en algún momento. Entonces, ahí ya hay otro mecanismo que gobierna. Incluso aquí puse como referencia otro de nuestros trabajos, que es mecanismos de mojado, Marangoni Contraction versus autophobbing. Ahí mostramos que hay una competencia entre pues este mecanismo de los flujos y un mecanismo de molecular. Entonces, pues sí, depende también de la actividad superficial de pues del líquido, ¿no? Ajá. Sí, porque en ese caso, por ejemplo, ahí no sabría cuánto tiempo duraría la gota, ¿no? Entonces se acabaría así súper rápido. Uno de los líquidos a lo mejor se evapora rápido y pues a lo mejor ya ni hay este efecto, ¿no? Nada más tienes un líquido. Entonces sí, hay muchos escalamientos aquí, ¿no? Por eso, pues es un problema muy rico porque pues tienes muchas escalas involucradas. Ujú.
¿Alguien más?
Ah, sí, el balance. En este caso, o sea, es general. No, en este caso, o sea, esta ecuación es general, puede ser para cualquier ángulo. Ajá. Sí. O sea, lo único que es como un balance de fuerzas, ¿no? Tienes una tensión superficial que jala hacia allá, una tensión superficial que jala con cierto ángulo, ¿no? Entonces nada más haces el balance en la dirección horizontal. No, y de hecho en la película va disminuyendo el ángulo de contacto hasta que se va a cero. Ujú.
Agradecemos a la compañera. La siguiente presentación es dirigida por Virgilio Alberto Aquino Cruz con el título de Resistencia al desgaste del acero IC 4140 nitrurado mediante dos procedimientos.
Sí, gracias. ¿Sí? Y por el lado. Ah, ah, gracias. Hola, ¿qué tal? Buenos días. Mi nombre es Virgilio Alberto Aquino Cruz. A continuación voy a presentar mis resultados preliminares de maestría relacionado al estudio de la resistencia al desgaste en un acero IC 4140 nitrurado por dos procedimientos. El contenido de la siguiente presentación menciona una introducción, un planteamiento del problema, una justificación, objetivos, procedimiento experimental, resultados, conclusiones y agradecimientos. El acero IC 4140 es un acero ampliamente utilizado en la industria. Este se utiliza para realizar diversos componentes como manufactura de herramientas, como árboles de levas, como cigüeñales, como piñones, espárragos, debido a sus propiedades mecánicas, como lo que es la maquinabilidad, la tenacidad y la resistencia al desgaste. Es bastante característico por sus propiedades químicas, lo que es alrededor de un 0.4% de carbono. Sin embargo, este acero tiende a presentar algún desgaste por contacto. En este caso, estos desgastes generan, son mejorables en el aspecto de desempeño tribológico. Estudios de Holmer y Erdemir han demostrado que alrededor de un 23% se pierde por contactos tribológicos, en este caso en el aspecto energético, económico y ambiental. Como mencionaba, el acero es ampliamente utilizado en la industria debido a sus buenas propiedades mecánicas y su maquinabilidad. Los tratamientos termoquímicos como la nitruración por sales son altamente utilizados debido a que mejoran las propiedades tribológicas, esto sin perder la tenacidad del núcleo, sin comprometer la tenacidad del sustrato, en este caso del núcleo del acero 4140. En la literatura hay escasa información respecto a mapas de desgaste de este acero sometido a estos dos tratamientos de nitruración. De estos dos tratamientos hablamos del tratamiento Tenifer y el tratamiento Tenifer QPQ. El objetivo general fue endurecer la superficie del acero 4140, como mencionaba, mediante estos dos procedimientos, los termoquímicos, lo que es Tenifer y Tenifer QPQ, para estudiar su efecto de la resistencia al desgaste y de esta manera poder generar los mapas de desgaste y en este caso determinar cuál es el tratamiento óptimo entre estos dos. Como tal, Los objetivos específicos fueron realizar 2 tratamientos termoquímicos del 4140, como comentaba en la técnica de nitrurado en sales Tenifer y Tenifer QPQ para obtener las capas de nitrógeno. En este caso se midió el espesor de las capas obtenidas de ambos tratamientos, se determinó la dureza mediante pruebas de indentación Vickers para estimar la capa de difusión, así como se determinaron las fases obtenidas por difracción de rayos X, y en este caso se realizaron las pruebas de desgaste por deslizamiento mediante pruebas de perno sobre disco para obtener sus coeficientes de fricción del desgaste específico y poder generar los mapas de desgaste. En este caso, la metodología que se siguió fue la siguiente. Tenemos nuestro sustrato acero IC 4140, el cual fue cortado de una barra de acero de 1.5 pulgadas con un espesor de aproximadamente 7.5-8 milímetros de diámetro. Este se realizó se realizó el proceso de metalografía, el cual consistió en lijar y pulir hasta un acabado tipo espejo, para posteriormente realizar ambos tratamientos, tanto el Tenifer y el Tenifer QPQ. Estos tratamientos fueron realizados a la misma temperatura, que fueron 580 grados Celsius, durante 90 minutos, y posterior a esto se procedió a realizar la caracterización, tanto estructural, lo que es microscopía óptica y difracción de rayos X, y la mecánica, lo que fue la microdureza Vickers. Por último, se realizó la caracterización tribológica de perno sobre disco. Como se aprecia en ambas imágenes, en la primera podemos apreciar lo que fue el primer tratamiento o el tratamiento Tenifer. Este tal cual, como mencionaba, fue durante 90 minutos a 580 grados centígrados en baño de sales de cianuro y cianatos. La segunda imagen que se aprecia es del tratamiento QPQ. Es un post-tratamiento del Tenifer, el cual consiste en sumergir, pulir y sumergir para que obtenga este color característico, que es como color oscuro, color negruzco. Y ahora bien, una vez que se obtuvieron estos 2 tratamientos, se continuó con el corte transversal para poder verificar cuáles fueron los resultados obtenidos de estos 2 tratamientos. Pasamos a la primera imagen, en la cual podemos apreciar una capa blanca, esta capa blanca que fue alrededor de 10 micras de espesor, en la cual se pueden apreciar las fases epsilon y gamma prima, así como en la segunda imagen o en la imagen B, la cual de igual manera podemos apreciar la capa blanca. Esta capa es un poco más gruesa que el primer procedimiento, que es Tenifer, así como se aprecia una ligera capa superficial que hace referencia o hace alusión al tratamiento QPQ, que en este caso es el óxido en la capa superficial. Para poder corroborar cuál fue la zona de difusión del nitrurado, o en este caso del proceso de nitruración, se realizaron las pruebas de microdureza, las cuales consistieron en comenzar las pruebas de microdureza en la capa blanca y de ahí bajar hacia el centro del sustrato. ¿Con qué finalidad? Para poder obtener la dureza y hasta qué punto esta dureza se estabiliza, que en este caso ronda para el tratamiento Tenifer de alrededor de 250 280 micras, bajo la dureza alrededor de 250 Vickers, ya que 250 Vickers es el promedio que tiene el acero 4140 en su dureza, de dureza tal cual. En el caso de QPQ, de igual manera se realizó el proceso de indentación de microdureza, en ambos casos de 10 gramos fuerza, solo que en el proceso QPQ se obtuvo una dureza mucho mayor de alrededor de 1000 Vickers. De igual manera, estas pruebas de indentación fueron hacia el centro del sustrato para poder obtener, o en qué momento se puede llegar a estabilizar, para que se compare con la dureza tal cual del acero 4140 sin ningún recubrimiento. Entonces, en la metalografía, en estos casos podemos apreciar que el tratamiento fue efectivo por las fases que se encontraron. Se comprobó de la siguiente manera: en el difractograma A, realizado al acero IC 4140, se encuentran los picos relacionados al 4140, el cual consta de la fase de ferrita. El segundo difractograma encontramos las fases, como mencionaba, epsilon y gamma prima, las cuales hacen referencia a epsilon, lo que es la capa blanca que se forma en la superficie del material, que hace referencia a la difusión de nitrógeno, así como gamma prima, que se forma de igual manera por la difusión de nitrógeno hacia el centro del sustrato. Y en el tercer difractograma se encontró, además de las fases epsilon y gamma prima, encontramos la fase de óxido de hierro, o en este caso lo que es la magnetita, que hace referencia a la capa superficial o lo que genera su característico color negro. En este caso, para generar los mapas de desgaste se realizaron se consideraron los siguientes parámetros. Se trabajó con una esfera de alúmina de 5 milímetros. Se realizaron las pruebas tanto para el acero base, el tratamiento Tenifer y el tratamiento QPQ. Esto a una velocidad constante de 0.15 metros sobre segundo, variando las cargas. Estas cargas se variaron con 5, 7 y 10 newtons para los tres casos. De igual manera, 250, 500 y 1000 newtons, en total dando 9 experimentos por tratamiento, 9 experimentos de cada uno de los tratamientos. Esto se realizó en condiciones de ambiente seco y una humedad de aproximadamente un 60%. Obteniendo lo siguiente, en la primera gráfica podemos observar los coeficientes de fricción que genera el color azul. Hace referencia al tratamiento Tenifer, que prácticamente es del doble del tratamiento QPQ. Incluso en los números es prácticamente el doble, 378 contra 775. Bueno, y en las imágenes A observamos la huella de desgaste de aproximadamente 500 micras que generó en este caso el desgaste de la bola de alúmina. En la imagen B apreciamos el desgaste que generó la bola de alúmina, pero para el tratamiento Tenifer, que inclusive se aprecia que es mucho menor que el acero sin recubrir, pese a que el coeficiente de fricción es mucho mayor. Y para el coeficiente C, para la imagen C, encontramos que el coeficiente, como mencionaba, el coeficiente de fricción es menor, así como se aprecia que la huella de desgaste es mucho menor que para las dos anteriores. Este es un ejemplo de la carga y la distancia menor de la prueba. Esta es una carga intermedia de una de las tantas pruebas que se realizaron. De igual manera, observamos que el coeficiente de fricción Tenifer se mantiene. De igual manera, el 4140 sin recubrir, y el QPQ, pese a presentar no una estabilidad similar a las anteriores, esto puede ser debido a diversos factores como el desprendimiento del material o el mismo recubrimiento que se va arrastrando a través de la superficie. De igual manera, en la imagen A se alcanza a apreciar que la huella de desgaste del 4140 es mucho mayor que las anteriores. Prácticamente QPQ no sufre en este caso de igual manera ningún daño hasta este punto. Y bueno, para la carga mayor y la distancia mayor de las cuales se realizaron las pruebas, se aprecia visualmente que en la huella de desgaste del acero 4140 sin recubrir es de aproximadamente, bueno, más de 1000 micras, lo cual ya es un desgaste considerable, así como el desgaste para el tratamiento Tenifer, de igual manera su huella de desgaste aumentó. Y en este caso podemos apreciar que el ancho de huella para el tratamiento QPQ a 10 newtons y 1000 metros es prácticamente el tamaño de huella que presentaban en las primeras pruebas ambos tratamientos 4140 y Tenifer. Y en este caso llegamos a este punto. El mapa de desgaste que se obtuvo después de las 9 pruebas realizadas es el siguiente, en el cual podemos apreciar que en el acero 4140 a una carga de 10 newtons o a una carga máxima y a una distancia realizada de 250 metros es donde más coeficiente de desgaste se encuentra, comparado con el mapa de desgaste del recubrimiento Tenifer, en el cual encontramos que el mayor coeficiente de desgaste se presenta en la carga más baja y en la distancia más baja. Este se estabiliza entre los 7 newtons y la distancia intermedia. Y por último, encontramos que la carga de 10 newtons y 250 metros de igual forma presenta coeficientes de desgaste un poco mayores. Y en el caso del tratamiento QPQ, observamos que el coeficiente de desgaste mayor se presenta en la carga menor y la distancia mayor, aumentando esta independientemente de que la carga aumenta y la distancia, el recubrimiento genera un menor coeficiente de desgaste tal cual. Y en este caso hacemos la comparativa de, de los tres mapas de desgaste, como se puede apreciar. Y bueno, como conclusión, observamos que los tratamientos termoquímicos, tanto Tenifer y Tenifer QPQ, fueron bastante eficientes en este caso, debido a que tanto generaron la capa blanca y aumentaron la dureza del material, así como su zona de difusión, la cual mejora el desempeño de este mismo. Eh, como tal, se comprobó mediante difracción de rayos X las fases presentes, en este caso, como comentaba, epsilon y gamma prima, que son resultado de una nituración, además de la capa superficial del producto de postoxidación. Y bueno, también cabe recalcar, el recubrimiento Q presentó los coeficientes más bajos y estables, y en este caso los mapas de desgaste y volumen perdido menores demostraron que los coeficientes o huellas menores se presentan en el tratamiento QPQ en un intermedio para Tenifer, y en este caso hay un mayor deterioro en el acero 4140. Y bueno, quiero agradecerle a las instituciones que me han apoyado en este caso, bueno, al Simposio, al Tecnológico Nacional, al Instituto Tecnológico de Tlalnepantla, al CECITI y al TEC de Monterrey, Campus Estado de México y Campus Santa Fe. Y por mi parte sería todo. Muchas gracias.
¿Alguna pregunta?
Buenos días.
Buenos días.
En el caso de la gráfica donde presentabas los coeficientes de fricción en función de las distancias, ¿cuál es la razón por la cual el coeficiente de fricción va cambiando conforme aumenta la distancia?
Debido al desgaste que se empieza a generar entre la huella, entre lo que es la superficie plana y lo que es la esfera de alúmina, la carga que se empieza, que genera respecto a la distancia o al recorrido que hace, es lo que empieza a generar este coeficiente de fricción.
Gracias.
Preguntas semejantes. Por ejemplo, ahí, ¿cómo me dice el desgaste? ¿A través del ancho de la huella?
Sí.
Ok, vale.
Este ancho de la huella se tomó de la huella total en 16 puntos diferentes de cada una de las huellas, promediando el desgaste, y en este caso el valor más aceptado de promedio fue el que coloqué en el dato que aparece en la imagen.
Ok. Y concuerdo con la pregunta del compañero. Por ejemplo, el coeficiente de fricción del QPQ brinca todo el tiempo. ¿Por qué brinca?
Pueden ser diversos factores. Uno de ellos es que hay desprendimiento del material y que inclusive puede funcionar como autolubricante. Entonces, por ende, no va arrastrando, sino que va generando una pequeña pérdida, que esto va haciendo que precisamente vaya brincando la esfera de alúmina sobre el material.
Ok. ¿No sería posible que tuvieras llevado la capa? Porque tu coeficiente de fricción se estabiliza con el 4140, ¿no?
Podría ser posible y no, porque al final del día en la imagen óptica se aprecia aún la capa y que inclusive la huella de desgaste es pequeña.
¿Hasta abajo alcanzas a ver todavía la capa?
Sí, resultados preliminares inclusive demostraron en NDS que sí aparece el tratamiento termoquímico.
Okay.
Sí, podría ser posible.
¿Alguien más? Agradecemos al compañero.
Gracias.
La siguiente presentación se titula Propiedades tribológicas de las mezclas de poliamida reforzada
aquí
con
está.
fibras de vidrio y butiral de polivinilo reciclado de parabrisas
Excelente.
automotrices. Por Isabela Ariadna Carmora Cervantes.
Hola, buenos días. Soy Arina Carmona. El título de mi presentación es Propiedades tribológicas de una poliamida reforzada con material de polivinilo reciclado de parabrisas automotrices. El contenido de mi presentación, por mencionar algunos puntos, objetivo, metodología y resultados. Un poco de contexto. Actualmente una de las grandes problemáticas es la contaminación ambiental. En ese sentido, lo que se busca en su mayoría es reducir el CO2. Por lo tanto, un estudio realizado por la Agencia Internacional de Energía hizo una estimación que para el 2050, una de las energías que más producirían CO2 sería en el uso eficiente de la energía. Me quiero ir para atrás, no puedo. No, sigue para adelante. Bueno, va, listo. Pues, sí, ya. Gracias. Es eficiente la energía. En ese sentido, con la tribología, una de sus gamas, lo que se busca es incrementar la eficiencia del uso final de la energía. ¿Cómo? Generando nuevos materiales y nuevos lubricantes, con nanocompuestos o lubricantes sólidos. En ese sentido, la industria automotriz es uno de los mayores consumidores de energía. De esa energía que consumen, únicamente el 30% lo utilizan para controlar la fricción. En ese sentido, otra estrategia de la industria automotriz para reducir este consumo de energía es disminuir el peso de los vehículos. ¿Cómo lo hacen o cómo lo están planteando hacer? Cambiando los materiales ferrosos por materiales poliméricos o polímeros compuestos. En ese sentido, en la industria automotriz, la poliamida 6 es uno de los termoplásticos más utilizados. Como sus propiedades tiene una buena resistencia mecánica, alta resistencia al desgaste, así como alta resistencia a la corrosión. A la poliamida comúnmente la reforzamos con fibra de vidrio para incrementar propiedades mecánicas, térmicas y eléctricas. Una de sus aplicaciones principales, ya con la fibra, es en las partes estructurales y eléctricas. En la parte de la tribología también tiene aplicaciones en engranes y rodamientos, sin embargo, estos son un poco más limitados. Por lo tanto, lo que buscamos es incrementar la resistencia al desgaste de la poliamida para expandir sus aplicaciones. En ese sentido, el butiral de polivinilo, o PEV, es un termoplástico con alta tenacidad y una buena adhesión. En la industria automotriz, principalmente se utilizan los parabrisas y todo lo que es vidrio reforzado. En ese sentido, existe la normativa europea Vehículos al final de su vida útil, la cual busca reutilizar y reciclar alrededor del 85% de los materiales en un vehículo. En ese sentido, el PEV y los parabrisas representan el 3% de sus materiales y particularmente hay aproximadamente 1 kilogramo de PEV en cada vehículo. Sin embargo, una vez que termina el uso con los automóviles, estos se desechan y, de acuerdo con la norma, se tienen que reciclar. Principalmente lo que se reciclaba era el vidrio y el PEV lo dejaban en vertederos de basura. De hecho, se estima, con un dato de 2021, que alrededor de 105,000 toneladas de PEV se desechan anualmente. Cabe resaltar que el PEV es un polímero altamente costoso de fabricar y de alto valor. Por ende, diversos investigadores empezaron a buscar aplicaciones o a estudiar PEV reciclado, ya que es un material que conserva sus propiedades después de ser reciclado. En antecedentes tenemos que autores como Bay y colaboradores exploraron las propiedades de impacto y mezclas de poliamida con PEV y ellos encontraron que cuando agregan un compatibilizador químico, sus propiedades de tenacidad incrementan. Esto nos dio la idea de que el PEV tenía una buena compatibilidad con la poliamida y aunado a que tiene propiedades semejantes al lubricante sólido, con bajo esfuerzo cortante en la dirección de deslizamiento y buena adhesión, podría ser utilizado como un lubricante sólido en la poliamida. El objetivo de este estudio es caracterizar una poliamida ingenieril reforzada con fibra de vidrio, mezcladas con distintas concentraciones de PEV en ensayo de desgaste perno sobre disco y reciprocante lineal, para estimar el coeficiente de fricción, la tasa de desgaste y los mecanismos. En metodología son polímeros. Primero realizamos una mezcla de poliamida con PB mediante moldeo por extrusión, inyectamos y en el primer estudio de perno sobre disco hicimos dureza short D, ensayo de desgaste de perno sobre disco y caracterizamos los mecanismos de desgaste mediante SEM. Para el ensayo de desgaste reciprocante lineal hicimos un análisis de la morfología de estos dos materiales, ensayo de tensión, dureza short, los ensayos de desgaste reciprocante lineal, para medir el desgaste, una perfilometría óptica e igual caracterizamos mediante SEM. Con resultados, podemos ver como la morfología del material, mezclamos dos polímeros y aquí podemos ver ambas fases. En ese sentido, estas muestras las metemos en nitrógeno líquido, las sacamos, las fracturamos y lo que podemos ver como pequeños hoyitos es PB disuelto, lo metimos a disolver en etanol. Entonces aquí podemos ver la diferencia entre las dos fases de nuestro material. Asimismo podemos observar cómo cuando agregamos el PB, el diámetro de nuestras partículas incrementa conforme agregamos el material. Ahora, nuestras propiedades mecánicas. La poliamida es un polímero relativamente rígido. Tenemos 4 gigas aproximadamente de lo que sería el módulo de Young. Cuando agregamos el PB, nuestras propiedades mecánicas empiezan a disminuir, tanto en el módulo elástico como en la resistencia tensil. La dureza short de algo semejante, vamos disminuyendo. En nuestros primeros resultados del perno sobre disco, cabe resaltar que a este lo utilizamos a una velocidad de 500 milímetros sobre segundo. En nuestros resultados de coeficiente de fricción de la poliamida, que en este caso es el negro, podemos ver cómo es un relativamente coeficiente estable. Cuando agregamos el PB, el coeficiente de fricción empieza a disminuir. En nuestro ensayo de desgaste reciprocante lineal, tenemos la velocidad mucho menor, 30 milímetros sobre segundo. Tenemos una poliamida igual, el negro es la poliamida, un coeficiente de fricción relativamente alto. Y cuando agregamos el PB, el coeficiente de fricción va disminuyendo. Del otro lado tenemos la caracterización de la pérdida de material, igual la poliamida es en negro, y podemos ver cómo con el 15 y el 20% de PB disminuimos bastante lo que sería la pérdida de material. Los mecanismos de desgaste en el ensayo de perno sobre disco, en general, relativamente son los mismos. Tenemos adhesión, tenemos fibra desprendida, fibra fracturada. Lo que cambia en ese sentido es qué tan alto, bueno, sí, la intensidad de los mecanismos. En la poliamida 0, que sería el A, tenemos fibra fracturada y tenemos material adherido en todo lo que sería el contorno de la huella. En el 10% tenemos una gran cantidad de material adherido, tenemos algunas fibras que se salen y tenemos fibras fracturadas adentro de lo que sería el material. En el 15% tenemos las fibras desprendidas, tenemos el material adherido y pequeños escombros de fibra. Sin embargo, aquí tenemos menos material adherido. En el 20% tenemos que las fibras ya prácticamente no salen y una menor cantidad de material adherido. Así como vemos que con el PB disminuimos la cantidad de material que se va desprendiendo. Cabe resaltar que es un ensayo de perno sobre disco, entonces la mayoría de los escombros tienden a salir de lo que sería la huella de desgaste. En el ensayo de desgaste reciprocante lineal, podemos ver los mecanismos son diferentes. En ese sentido es el sentido del desgaste. Tenemos la huella en la poliamida 0, poliamida sola. La fibra se queda embebida en lo que sería el material adherido. Tenemos poca fibra suelta, tenemos unas cuantas cavidades. En el 10% es donde tenemos una mayor cantidad de fibras fracturadas, escombros de fibra, y tenemos una menor cantidad de material adherido. Entonces tenemos una mayor fibra expuesta, lo que resulta que tenemos una partícula que puede llegar a ser abrasiva. ¿Y cómo lo vemos? Que en la bola del 10% tiene unas pequeñas marcas de abrasión e incluso una picadura. En el 15% de PB tenemos una mayor cantidad de material adherido, las fibras están completamente embebidas en el material. En el 20%, las fibras ya prácticamente no se rompen, conservan su posición original, poco material adherido y pocos escombros de fibra. Con respecto a las propiedades de desgaste, particularmente reciprocante lineal, podemos observar cómo el coeficiente de fricción, el 10% se mantiene igual que el de la poliamida, pero va disminuyendo con 15 y el 20% de PB. El volumen perdido disminuye de manera considerable, así como la tasa de desgaste. Como conclusiones, en la configuración de perno sobre disco, el PB 10% tiene menor coeficiente de fricción asociado a la ausencia de escombros en la huella de desgaste. En reciprocante lineal, las mezclas de 15 y 20% demostraron una mayor resistencia al desgaste, un menor coeficiente de fricción en comparación con la poliamida original. Las mezclas 10% presentó una mayor cantidad de volumen perdido, disminuyendo la resistencia al desgaste en comparación con la poliamida. Finalmente, la adición del PV a la poliamida con fibra de vidrio podría expandir sus aplicaciones para incrementar el tiempo de vida de los componentes, así como darle un segundo uso a lo que sería el material de polivinilo reciclado. En perspectiva de trabajo, analizar el efecto de compatibilizadores químicos para, en el caso de estos dos materiales, para generar una mezcla más sensible, incrementar propiedades mecánicas de la mezcla, agregando micro o nano refuerzos para incrementar las propiedades y ver si mejoramos aún más la resistencia al desgaste. Y por último, evaluar el efecto de diferentes parámetros de inyección, por ejemplo, temperatura, presión y velocidad, sobre la morfología y la resistencia al desgaste de estos materiales. Algunas referencias utilizadas para esta presentación y nuestros contactos por si alguno está interesado. Y muchas gracias por su atención.
¿Alguien tiene alguna pregunta?
Cuando presentaste tus mecanismos de desgaste, me dio curiosidad que a mayor concentración de PVB tus fibras se rompían menos. Me da curiosidad, bueno, ¿cuál es el efecto que tiene el PVB sobre tus fibras para que pues, las proteja?
Ok, podemos poner en grande la presentación por... No sé, mejor salir, perdón. Ok, va. En una de las
Alan.
diapositivas, ¿me la puedes poner, por favor? Y poner la 25. Eso tiene que ver un poco más con lo que hace el PV. El PV forma enlaces a través del grupo hidroxilo y es por su principal aplicación que se adhiere a las fibras de vidrio, tiene la cualidad de, la 25, tiene la cualidad de adherirse a lo que sería el vidrio. En ese sentido, el PV tiende a adherirse a las fibras de vidrio. Cuando incrementamos el porcentaje de PV, hay más material que se adhiere a las fibras de vidrio y empieza a generar una película lubricante sobre la huella. Particularmente, conforme agregamos el material, tenemos mayor película lubricante sobre lo que sería la huella de desgaste y eso ayuda a que se desprenda menos material. Asimismo, recubre las fibras de mejor forma, digámoslo así, o recubre en mayor cantidad las fibras, evitando que éstas se fracturen y se suelten. En este caso no tenemos tanto efecto de las fibras porque estamos en perno sobre disco y las fibras que se desprenden o se fracturan van saliendo de la huella. Caso contrario que en el reciprocante lineal, las fibras que se fracturan permanecen en la huella. Entonces, el PV se adhiere debido a los enlaces que genera con la fibra y genera una película lubricante.
Ok, de acuerdo, muchas gracias.
¿Alguna otra pregunta?
Buen día. De manera general, ¿cómo es el proceso de agregar el PVB en la matriz de poliamida?
En sí, los polímeros vienen en forma de pellets, en cubitos. Entonces, ya teníamos, bueno, nosotros nos donaron el PVB reciclado, lo cortamos, en general es el parabrisas, el recorte del parabrisas, lo que la industria automotriz ya no ocupa, en parte ese recorte, lo donan, nosotros estamos recortándolo y lo destinamos en peliculitas, digámoslo así. Entonces lo mezclamos con los pellets de la poliamida y lo extruimos. Tenemos un extrusor. Aquí está. Entonces, agregamos los pellets aquí en lo que sería la tolva. Este es un tornillo sin fin que está a determinada temperatura. Cada material tiene su temperatura para mezclado. En sentido, mezclamos estos dos materiales mecánicamente, digámoslo así, en el extrusor a 250 por la temperatura de fusión de ambos materiales y ya nos queda un material relativamente homogéneo.
Okay. Y este efecto de agregar el PVB, ¿has revisado si modifica el comportamiento hidrofílico de la poliamida? Si lo vuelve más hidrofóbico o algo así.
En general, la poliamida es tiende a absorber mucha agua. Sí, en general la poliamida tiende a absorber agua. El PVB tiene, parte de su estructura está dividida en tres partes, tiene tres monómeros el PVB. Y uno de sus monómeros tiene a absorber agua, pero los otros dos no. Tal cual pruebas de absorción de agua no hemos hecho, pero sí está en nuestros planes futuros hacer pruebas de absorción de agua. Podría ser que la disminuyera porque no tiene tanto afinidad a absorber agua, pero nos falta hacer las pruebas.
Ok, gracias.
¿Otra pregunta? Ok, agradecemos a la compañera. La siguiente presentación es impartida por Juan Rodrigo Laguna Camacho, titulada Un estudio de desgaste causado en una herramienta de arado de disco.
Este con este adelanto y este es el apuntador y con el otro. Sí. Bueno, buenos días. Mi nombre es Juan Rodrigo Laguna Camacho, su servidor. Vamos a presentar o voy a presentar el trabajo titulado Un estudio del desgaste causado en una herramienta de arado de disco. Este trabajo les tengo que mencionar que es la primera etapa de un proyecto de investigación que tiene que ver con el incremento de la resistencia al desgaste de herramientas de arado. Y lo queremos hacer a través de diferentes tratamientos térmicos, termoquímicos o recubrimientos. Entonces, en una primera etapa, lo que queremos hacer es identificar los mecanismos de desgaste. Queremos caracterizar las herramientas de arado de disco, de vertedera y de cincel, ¿sí? Presentamos también el doctor Ezequiel Alberto Gallardo Hernández, que es mi asesor de la estancia postdoctoral académica, el doctor Manuel Vite Torres, que es mi coasesor, y también académicos de la Universidad Veracruzana que apoyan el proyecto. Bueno, les quiero presentar el contenido de cómo va a estar integrada la presentación. Tenemos una breve introducción acerca de las herramientas de arado, el procedimiento experimental y posteriormente presentamos resultados, la identificación de mecanismos de desgaste, los perfiles de desgaste, el trabajo a futuro y las conclusiones. Una pequeña introducción y muy breve tiene que ver con que las herramientas de arado normalmente están expuestas a partículas o al contacto de partículas del suelo, que pueden ser piedras, arcillas, limo, arena, cuarzo, segmentos de vidrio, pero también puede ser hierba, pasto y maleza. Esto lleva a que normalmente las herramientas de arado están expuestas a desgaste abrasivo severo, lo que conocemos con el término de gogging, ¿sí? Entonces, por eso fue importante poder desarrollar este tipo de proyecto. Nosotros hemos venido trabajando con erosión por impacto de partícula sólida y también hemos venido trabajando con abrasión de 2 cuerpos, de 3 cuerpos, y esto fue interesante. Me he dado cuenta en la revisión bibliográfica que varios de los trabajos de investigación se enfocan en el desgaste en cuchillas de arado de vertedera, las herramientas de cincel, las cuchillas de los rotores, las cuchillas y las rejas de arado. Entonces tenemos una buena área de oportunidad para poder mostrar el desgaste que se genera en un disco de arado. De forma muy breve, la caracterización tribológica se realizó en la herramienta de arado de disco. Nosotros tenemos una hilera de 11 discos y nos fue donado el disco de la parte media. Entonces, este disco, aunque parezca pequeño, es bastante grande, es bastante complicado de manejar. Tiene un diámetro exterior de 560 milímetros, 56 centímetros. El diámetro en el centro, el del eje, de 40 milímetros. Tiene un espesor en el borde de 3 milímetros, aproximadamente 1/8 de pulgada. Y el espesor cercano al centro, al eje, es de 1/4 de pulgada. El lugar de cultivo es Chichimantla II, en Acuetampa, en el estado de Veracruz. y el tiempo de producción aproximado fue de 3 años. Es el tiempo de servicio de la herramienta de arado. La caracterización tribológica, lo que hicimos, como lo podemos ver en esta imagen, pues tuvimos que cortar. Primero empezamos con arco con cegueta y posteriormente tuvimos que utilizar la herramienta de corte y un poco alejándonos de la zona de corte fue que hicimos más bien la caracterización de los segmentos. En esta primera parte primeramente hicimos una inspección visual, tenemos una muestra y nos pudimos percatar de que podíamos ver algunos cráteres y algunos agujeros. Nosotros nos referimos a cráteres, algunas cavidades que tienen mayor tamaño y los agujeros, cavidades que tienen un tamaño más pequeño. Posteriormente, empleando el microscopio óptico modelo 1200 radical, pudimos iniciar con la identificación de los mecanismos de desgaste. En este caso tenemos o podemos observar cráteres, algunos agujeros y algunas partículas incrustadas que tienen una característica muy particular porque son partículas transparentes, que bien podría ser algún tipo de mineral o podría ser vidrio simplemente. En esta siguiente imagen, algo que me faltó comentar es que la herramienta tiene una particularidad, tiene una superficie cóncava, que es muy importante porque es la que hace el primer contacto con la tierra, levanta la tierra, la remueve, la voltea y la deposita sobre el surco, ¿no? Entonces, ese lado cóncavo es muy importante y pudimos identificar un mecanismo de desgaste normalmente conocido como la acción de arado, ¿okay? Donde podemos tener o donde podemos ver material apilado o acumulado hacia los lados y también en la parte frontal con respecto a la dirección o al movimiento de la partícula. Además, bueno, pudimos percatarnos de algunas partículas incrustadas, algunos residuos de desgaste. Esto fue con la microscopía óptica, fue la primera parte. Con respecto a la microscopía electrónica de barrido, pudimos identificar otros mecanismos de desgaste. Algunas grietas que son muy claras, pudimos percatarnos de algunas partículas orgánicas adheridas sobre la superficie de la herramienta. Prácticamente todos los segmentos de cada una de las zonas que analizamos están cubiertas con partículas orgánicas. Y pudimos tener algunos EDS que fueron muy interesantes porque tuvimos elementos que son orgánicos. ¿Sí? En esta parte, la que estoy mostrando, tiene que ver con una zona cercana al borde de la herramienta de corte y podemos ver en su sección transversal, en la parte de abajo, la base que es el acero, que tiene una composición elemental muy básica, muy común, con carbono, silicio, manganeso y hierro. Y en la parte de arriba, en esta parte que hicimos el análisis en esta capa, pues es una capa oxidada y tenemos una punta, un pico de oxígeno, ¿ok? Con elementos orgánicos que fueron muy importantes. Además, pudimos apreciar mecanismos de desgaste que tienen que ver con el desgaste por abrasión en 2 cuerpos y 3 cuerpos también, y por supuesto con la erosión por impacto de partícula sólida, algunas acciones de arado con material, con algunos residuos sobre la ranura, y también algunas indentaciones que son irregulares, aparte de más partículas adheridas sobre la superficie de la herramienta. Además, bueno, otro trabajo que hicimos o que queríamos, como vimos en la inspección visual primaria, pues queríamos tener una perspectiva de cómo era la superficie del disco de arado. Entonces, lo que hicimos fue que a través de un estudio de perfilometría pudimos obtener algunos perfiles de desgaste y pudimos determinar el ancho y la profundidad de algunos cráteres y también de algunos agujeros. En este caso, la dirección de deslizamiento fue de forma longitudinal a la muestra y pudimos obtener este tipo de perfiles, tanto del lado cóncavo como del lado convexo. Y posteriormente también lo hicimos con respecto al ancho del espécimen. Y también obtuvimos algunos perfiles y pudimos determinar el ancho y la profundidad de los agujeros y de los cráteres. Con respecto al trabajo a futuro, tenemos todavía que llevar a cabo algunos ensayos de dureza sobre los segmentos con respecto a la norma ACTM ET 384. Tenemos que llevar a cabo algunos estudios de rugosidad, caracterizar la tierra. Tenemos la idea de caracterizar la tierra que tuvo contacto con el disco de arado, completar un trabajo que, bueno, es parte de los productos que tenemos que entregar en la estancia postdoctoral académica, y realizar también ensayos de erosión-abrasión en muestras sin recubrimiento y con los recubrimientos sugeridos obtenidas del disco desgastado, ¿no? Del disco desgastado. Les tengo que mencionar que, bueno, vi un póster donde se ocupa el borurado, que es un tratamiento termoquímico. Podría ser una de las opciones que se pudiera emplear para poder incrementar la resistencia de estas herramientas, ¿no? Además, bueno, queremos caracterizar tribológicamente dos herramientas de arado más, de vertedera y cincel, que son muy, muy interesantes. Y por supuesto, aparte de la difusión que estamos llevando a cabo en eventos académicos, pues también tenemos que llevar esta difusión y esta divulgación al sector agropecuario. Sí, queremos que esta sea una línea de investigación, no solamente en el presente, sino a futuro, y que pueda ser más amplio los estudios. Como conclusiones, bueno, pues como ustedes pudieron ver, obtuvimos mecanismos de desgaste muy similares a lo que es la abrasión, el gogging, ¿no? La abrasión severa es uno de los mecanismos de desgaste. Acciones de arado, picados, partículas adheridas o incrustadas sobre la superficie fueron fueron característicos. Y en los perfiles de desgaste tuvimos la posibilidad de conocer la morfología de las superficies, ¿no? Del desgaste, de cómo se está produciendo. ¿Sí? Entonces tenemos una perspectiva más clara, una idea más clara de cómo se comportan las herramientas de arado. Algunas referencias que hemos estado empleando para que se queden como posibilidad de ver en cualquier momento. Y me gustaría agradecer, como les comentaba, esto es parte de un proyecto financiado por la CCITI, es el nombre del proyecto, a mi asesor, al doctor Ezequiel Alberto Gallardo Hernández, a mi coasesor, el doctor Manuel Vite Torres, y a los académicos de la Universidad Veracruzana, de la Facultad de Ingeniería Mecánica y Eléctrica de la región Poza Rica-Tuxpan, que también participan en el proyecto. ¿Sí? A la Universidad Veracruzana y a la Facultad de Ingeniería Mecánica y Eléctrica por darme la posibilidad y la autorización para poder tener este año sabático, y a los estudiantes de la maestría y del doctorado en Ciencias en Ingeniería Mecánica del Politécnico de la CEPI, ESIME, en la unidad Zacatenco, que incluso están aquí presentes. Y bueno, pues me han apoyado bastante para poder ir logrando estos resultados. Bueno, pues les agradezco mucho su atención, su presencia. Si tienen alguna pregunta, con toda confianza. Gracias.
¿Alguna pregunta?
Buen día, doctor.
Buen día.
¿Ustedes utilizaron discos ya utilizados? O sea, ¿lo tomaron directamente de la máquina y lo caracterizaron?
Sí. Fuimos a la comunidad. Pudimos tener la posibilidad de que nos donaran el disco de la parte media, que ya había tenido 3 años de servicio. Entonces, digamos que ya tenía cierto deterioro, y eso nos dio la posibilidad hacer el análisis de la identificación de los mecanismos de desgaste.
Ok, ¿y de qué manera se podría cuantificar el desgaste, o sea, la tasa de desgaste, o nada más observar los mecanismos?
Esta pregunta es muy interesante. De hecho, una de las tareas que tenemos y de los trabajos que queremos llevar a cabo es que podamos cuantificar mediante la pérdida de masa, pero que lo podamos hacer en el sitio. Ustedes saben que podamos trabajar a lo mejor durante una semana o más tiempo, que podamos someter la herramienta con cada uno de los recubrimientos que vamos a sugerir en la tierra, ¿no? Y que se ponga a trabajar durante largas jornadas durante el día, a lo mejor 5 días seguidos, a lo mejor 2 semanas seguidas, y lo podríamos cuantificar mediante la pérdida de masa. Uh-huh.
Okay.
Es uno de los trabajos es uno de los retos que tenemos. Estamos buscando la forma de que nos puedan rentar, ustedes saben lo que es el tractor, lo que son las portaherramientas para que podamos llevar a cabo ese tipo de trabajo.
Gracias, doctor.
Gracias.
¿Alguna otra pregunta? Agradecemos al presentador.
Gracias.
Esta fue la última presentación del día de hoy. Nada más, ahorita tenemos un coffee break y posteriormente tendríamos los cursos, los cuales los invitamos. Sería la continuación del curso de Introducción a la Tribología y Tribocorrosión y el curso de cómo publicar un artículo científico. Gracias.
Thank you, sir. Good. Okay. ¿Puedes empezar? Ah, gracias. ¿En inglés está bien? Ok, gracias. Porque Daniel me dice, no, no. Necesito hablar en español. Okay. So this is me again, Samir Awadi from the University of North Texas. Thank you again for inviting me to give 2 talks today. Today, or this talk, I'm gonna wear the hat of an editor. So I've been working for Elsevier, and more specifically for Surface and Coatings Technology, for 10 years now as an editor. I'll be editor again next year. I don't know if I'm gonna be editor after that, but I have a lot of experience with editing and all that kind of stuff. So today I'll talk about our journal, steps involved in publishing in a journal, publishing ethics, generative AI. This is the only part that's new from last year. They just sent me their new stuff, which is really cool. And then a summary. So journal organization. So I work for Surface and Coatings Technology with Elsevier. Elsevier is the largest publisher in the world. It is located in oh, I don't have. Sorry? And the richest, yes. No, I don't have well, it's fine. I don't need it. It's not they are the richest. They are also located in the Netherlands. Okay. And my talk today is more for students and young researchers, just to see how to get published. So a publisher is my boss. I have a new boss now. She's in charge of 11 journals, including of Surface and Coatings Technology. Okay. Thank you. Thank you. So the publisher appoints editors, provides the editorial infrastructure, promotes journals to readers, and does all that kind of stuff. Editors. So I'm one of 10 or 11 editors at Surface and Coatings Technology. We define the aims and scope of the journal. We're the ones that send you emails to review, or ask you, or if you submit a paper, we're the ones that sort of look at it first before we send it to reviewers. We accept or reject papers, and we communicate with you about your paper. Most of us, the way we communicate is, it's already written, the paper, like the response is the same. We just go, but sometimes we change things, you know, if we can change things. Oh, thank you. Oh, no, this doesn't work. Okay. All right, so these are the editors for Surface and Coatings Technology. As you can see, we have people from all over the world that are represented. So the Brazil, Argentina for South America, we have India and the United Kingdom. This is gonna change a little bit in about a year. And in 2024, we had almost 1,000 publications, so 1,000 published papers. Our impact factor has been rising. 6.1 is quite good. It's actually really good. The site score 10.4 is also very good. And I'm going to mention like what that means. So this is a very good journal. To me, it's the premier journal for coatings and surfaces. Okay. This now doesn't work. Okay. What is an impact factor? The impact factor for 2024 is 6.1. What does it mean? In 2024, you look at all papers published in 2024, and you look at all citations of articles published the 2 years prior to that, so 2022 and 2023. You calculate that number, and then you divide it by the number of source items published in 22 and 23. So if you get 6.1, let's say 6, that means every article that was published in 2022 and 2023 was cited 6 times on average in 2024. Okay? And that's a good number. So what do you need to do when you look at paper, like when you want to submit your paper? You need to know the aims and scope. Why? Because half of the papers that we reject are due to the fact they're out of scope, which means they don't satisfy these requirements for processing or properties. For example, processing, we look at physical and chemical vapor deposition techniques, plasma spray, surface modification, etc. We exclude paint. And for performance, we look at properties such as friction, wear, corrosion, hydrophobicity, all these things, functional things for environment, energy, and medical applications. But we exclude anything that's device aspect, including optical or electrical properties. Those have their own journals. We don't want these paper, like we usually don't accept these papers. So if somebody submits a paper on optical properties of a materials, it's going to be rejected right away. Okay. Preparing a paper. Oops. Sorry. So the most important requirements for publishing a paper are, number one, originality. If the work is not original, somebody else has done it, there is no point in publishing it. So you have to make sure it is original. And that originality sometimes could be a gray area because there is incremental originality and there is like real original work. And that's where you have to think, well, do I submit my paper to a journal that has an impact factor of 2? Or do I send it to an impact factor of 10? If something is amazing, you can submit it to a much higher impact factor journal. If something is incremental, I would send it to 2 or 3 or 1 even, okay? So does it advance significantly the field? Does it have clear context and relations to previous work? Appropriate methods and conclusions, readability, so the English language is really good. So it has to be written well and presented well, and studies that meet ethical standards. So there is no plagiarism or copying from somebody else or just using ChatGPT only, or which I'll talk about those things later. So when you start writing your paper, you think about who's going to read my paper. To me, the most important one eventually is going to be your reader. But you're also going to have an editor that's going to look at it. Reviewers are going to look at it. And so those are the people you have in mind. How do I build your article? Your article is like you telling a story. Sometimes as scientists, we go and dig deep into details and we don't think of what is the story I want to tell. And so it's really important to think always you are trying to tell a story and then build from there. So this is the structure of an article, how you're going to write it. And I'll go one by one shortly. But to build an article, the way I tell it to my students, start thinking of your story first. Then start with your figures and tables, basically your data. So you put your data in the way the story, you want to build your story. So I tell my students have figure 1, figure 2, figure 3, figure 4. In material science, a lot of times if you're doing experiments, you start maybe with X-ray or your system setup, and then your X-ray data to look at the structure, and then other stuff later. For example, this is just as an example. So once you do that, then you go and write your methods, results, and discussion. Then at the end, you write your conclusion and the introduction. and then the title and abstract. I don't always do it like this. I always start with this, but sometimes I start with the intro. For example, when my results are not all there, I tell my students, start writing the introduction already, okay? So, but anyways, figures and tables are critical because a picture is worth 1,000 words. That's really what's gonna set your story right. That's the results are the driving force of your publication, and that helps you formulate your story. The methods are sort of easy. Somebody who has published 50 papers or more knows, or your experimental methods are not going to change much. You're using the same equipment, you're using the same stuff. So a little, not, I wouldn't say plagiarism, a little bit of redundancy between one paper to your next paper is not a bad thing. So that's not self-plagiarism. You're going to rewrite it a little different than your previous paper, but you cannot change it so much because it's the same method. So you describe what the so you do the include detailed information, describe the equipment you're using, etc. And usually this is not a big flag like for editors. Results and discussion: be clear, highlight your main findings, feature any unexpected findings, and discuss what the results mean. The conclusion: write it in a clear and concise fashion and provide a summary of the work at the end. Then the intro is really crucial. Why? The introduction is where you're telling the reviewer and the editor why this paper is new. So what you do is you start by referring to all previous research, and then you're going to say, well, but this is missing, like something is missing, and I'm going to fill that gap because I'm going to push the envelope for people to have new knowledge. And so you're going to address what the problem that hasn't been addressed before, without saying too much. Oh, this is the first time. A lot of reviewers and editors don't like that saying this is the first time, because everybody that publishes, this is their first time. You're assuming that this is their first time, so don't use those words all the time. But then you build a case at the end, your last paragraph or 2 paragraphs, up to you. That's where you're saying, hey, I'm doing something new. This is why it's new, and this is how I'm going to do it in a very brief fashion. Okay. Then you have a title. Have for your title the fewest possible words, but adequately describe the content. So not just 2-3 words, but maybe a little, like a sentence, like 10 words or something like this, because you need it to be descriptive, that identifies the main issue, and don't use abbreviations in your title. So don't put, for example, I do PLS, pressureless sintering. Don't put PLS, put pressureless sintering. So don't use acronyms. The abstract, write it it's probably the most crucial piece of your paper. Why? Because that's the first thing anybody's going to read, your abstract. And already, many people have already made up their mind sometimes. I mean, 80% of people, like, I don't know if this is novel or not just by reading the abstract. Again, people should not just jump to conclusions, but if people don't have a good view of the work just by reading the abstract, it's going to be hard to convince them later that this is worth publishing. So make sure you write an amazing abstract. The authors now. When you have a paper, nowadays, it's not just one person that goes and does everything. You have students, you have researchers, you have collaborators, and sometimes it's hard. Like, do we include all these people or not? So the most important ones are the first author and the last author, usually. The first author is the one person that writes the paper, and the last author is the advisor, if the advisor doesn't write the paper in general. And then the rest of the people are somewhere in between. Now, you have to make a decision, and especially the first author and the last author, who to include. So for example, for me, and it's a gray area, right? If somebody does, for example, on my ultra high temperature ceramics, just hardness test, not nano indentation, where you don't need like I use somebody else's equipment. That person usually doesn't ask me, hey, add me to your paper, because that's a simple equipment that doesn't cost much, doesn't need your expertise. And so usually I don't include those people, and I can acknowledge them at the end, right? But if anybody that contributes scientifically, they should be included. And sometimes you're not sure, ask that person. So your team can say, hey, I was going to add you to this paper. What do you think? Okay. All right. Acknowledgements, you acknowledge, so those are not authors. At the end of the paper, you acknowledge advisors, financial support, if somebody proofreads your paper, etc. And then you add keywords. So have 4 or 5 good keywords, so that because in the search engine, that's how people find your paper. So they cite you, and that's good for you, because when you get cited, your H index goes up. You know the game, right? Now, references. This is also a cool one. This is what Elsevier says. Do not use too many references, and do not use too little. What's a good number, according to you? I mean, I know it's a gray area. Okay, so but what's a good number? Bunch of, no, 45. Okay, 20 to 45. I like those numbers. That's really exactly perfect. If you have too few, it means you haven't done a background research to look for your intro. And if you write too many, it means every little thing you're putting 10 people, or you're adding yourself, and and there's a lot of work in that field. So it doesn't give a good, unless you're doing a review paper, I wouldn't have more than about 45, you know, something like, or maybe 50 at most. Okay, avoid excessive self-citations. A few people, and as an editor, I see them, the same people, they put 10, 12 of their papers in that 25, you know, like, and that's not acceptable. So that their H index goes up. Okay, so some people are very notorious for doing this. I like having self-citations, but maybe 1 or 2, no more than 3. Avoid excessive citations from the same region. This is what Elsevier says. Well, that means, for example, a paper from China, if they only cite China, well, it doesn't mean that just that area does that kind of work. There's work from other parts of the world. You know what I'm saying? So, okay. Cover letter, you write a cover letter. I don't usually read them much, because everybody says, oh, my work is new and novel and da-da-da-da-da. So I look at the content instead. So this explains why this is important, that hasn't been submitted anywhere else. And then your peer review process. So the peer review process, generally editors do a first check. Yeah. Sure. Sure. Yes. Okay. Okay. That's true. Conclusion. Yes. I like that. And how is abstract also different from that as well? You know what I'm saying? Like that's also, yeah. Yes. Yes. Yeah. Now, very good point, and I agree with you 100%. So the conclusion, you're going to have a little bit of a, okay, we've done this, or the summary, or whatever. It's called conclusions in their journal. And then you conclude with results. Abstract is more results, and it's more short. And you can have maybe a sentence that's, hey, I'm doing this, and then you delve into the results right away in a very brief fashion. No, but I agree with you 100%. Yeah, thank you. Yeah, yeah. Yes. 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 Editor also does the same thing. I don't, I look at 35 papers a month, which is a lot. I can't review them and read them like carefully. I read the abstract and then I go quickly and see if they're following like the requirements, you know, like the way they're doing the figures are good and all that kind of stuff. And then after that, I send it to reviewers. I usually don't read the conclusions because they're usually a little repetitive, but I look at the abstract more. But yeah. Now, desk reject. I don't do a lot of desk rejects, and I'm also a little bit of on the nicer side of the reviewers, of the editors. I'm sorry. Okay. We have now an editor that does the desk rejects only. And then if it's not desk rejected, he sends it to us. And then we go and look at the paper. Sometimes I desk reject as well, but it's very rare because he does a really good job. But sometimes it's like, I don't know. Anyways, but the desk rejects are mostly because it's out of scope, it's not well written, or it's not novel. And it's so obvious that it's not novel. So somebody's like, I'm doing titanium nitride, and I'm looking at the hardness and the wear of titanium nitride. People have done that for years and years and years, and there's nothing new. And so that, you know, like, you know, after the initial check, we send it to reviewers. Then I get the reviewers' reports and then make decisions. If there is any doubt, I can ask more reviewers. Sometimes I review it. Sometimes I'm not the best person for reviewing it either. And sometimes it's hard to make a decision. You get a reject and minor and then one major. And I was like, I don't know what to do. So I try to look at them and try to, for the best of my knowledge, to make a right decision. Is that right decision always the correct one if you had another editor? Probably not, but most of the time it is. But there are a few cases. So don't get upset if your stuff doesn't get gets rejected. I get rejected. I mean, all of us get rejections. Okay, so then once we have that, we inform the authors, and these are the choices. So not the choices, the potential things that happen is, one, you get a rejection because of lack of novelty, for example, or because of ethical concerns, etc., or you didn't use the guidelines of their journal, or poor language or image quality, etc. And the editor lets you know why your paper was rejected. We use these tools to look for plagiarism, to look for also who is a good reviewer for us. Before, I remember 10 years ago, I used to go and look for who works in this field. Now I don't even need to do that. I still do it sometimes, but we have like on the website, it looks for the right people that are working in this field. Okay, this is if you want to become a reviewer, you can just send an email and you can become a reviewer. We get those from time to time and we add the reviewers. Yeah. Mm-hmm. That's a personal preference, and personal preference depending on the paper, depending on the reviewers, and depending on if that's a field of the editor or not. So I do look into that, but if, say, for somebody from a country only chooses 3 people from that country, I assume they know each other, and I would not look at that. But if they're like, hey, 3 names from different places that are truly known, or even they don't have to be very well known in that field, then I'll pick 1 or 2, or even all 3. And because when I send, let's say, 10 requests, I get maybe 2 or 3 that are going to review, and 7 are not going to review. So adding those 3 to other ones, usually most reviewers are honest, and I trust the system, because most scientists are not going to be there. No, I don't want this, or I'm going to just help my friend. I mean, it's so everybody. I trust in the scientific community that they do a good job, and yeah. Mm-hmm. Yes. Yes. I've had that. Okay. Yes. I've had that in. Okay, I cannot tell you. No, you cannot. You know the last part of my previous talk? I sent it to the Journal European Ceramic Society, which is Elsevier. And I had 3 reviews. 2 were major, and 1 was no. This is like a reject. And the review and the editor rejected it. I'll be honest with you, that was one of my. I wrote like 130 papers. One of my top 5 papers in my career. And I know that better, because I'm hard on myself, you know what I'm saying? And they did the same thing. Oh, why don't you send it to this open access? And I'm like, no, forget it. So I sent it to a different journal. Sometimes it's worth fighting the fight and send the editor and say, look, I don't agree with that. This, and to me, if I'm the editor, if you email me and say, you spend time writing a response, your time is also very valuable. I look into that, and I maybe resend my decision and send it to new reviewers as well, and review it myself. Some editors don't do their job. They're, you know what I'm saying? Like, and some are just like, reject is reject. I'm sorry, I'm not going to do anything about it. Right? To me, reject is not a final reject. If you send me a long email explaining why the other reviewers were wrong about something, I will resend it. That's me. But not everybody does that. Economics has entered, and I agree with you on that. So they go to one that has an impact factor of 0.8. Send there, and it's open access, and you pay 4,000 euros, because it's in Europe, 4,000 euros. And I'm like, I don't pay 4,000 euros. I don't care, even if it doesn't get published. I agree 100%. Yes. It's a business. And offline, so even with like they have MDPI from Asia, and then Elsevier is like, oh, look, they're getting a lot of stuff done. How do we counter them? And so they're doing these things. But MDPI also, you get your reviews really quickly, within like sometimes a week or 2. And then I'm like, I don't know if I trust that either. Anyway, so editorial decision. So let's say I review about 350. I handle, not review, handle about 350 to 400 papers a year. How many are accepted as is? Yeah, 2, 3. So most of them no. Okay, so on average about 2, 3 a year. Major or minor a lot, and rejects. And rejection rates for surface and coatings technology is probably 80% or 78%. Maybe I reject a little less. But that includes out of scope, because half of them are out of scope. Once it's in scope, I would say you have 40 to 50% chance of making it not being rejected. So if you have a major or minor revision, you carefully read the reviews, the reviews, and you respond to all points, and you perform additional experiment if necessary. Sometimes it's not possible, and sometimes they're requested. So this is an example of a response letter for a paper that I submitted to Journal of Vacuum Science and Technology. This is my response letter. We would like to thank the editor, da 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 da. And then here are the reviewers' comments, my response, another reviewer's comment, response, etc. And that's how you do a response. And this is very helpful. And just to give you an example. Okay. Now I'm going to talk about publishing ethics, and then I'm going to talk about AI. The AI part, I just got it, the new version of what they have, so, which is fine. So publishing ethics. These are things that are misconduct, ethical misconduct. I personally don't use with ethical misconduct. If there is ethical misconduct, I send it to the editor-in-chief, and the editor-in-chief deals with it. So we have an editor-in-chief, and we are like 10 editors, right? Before we didn't have an editor-in-chief, like 7 years ago, we all dealt with this. So the misconduct is data fabrication, data falsification, plagiarism, omitting authors, changing author affiliation, and then multiple submissions. You submit the same paper to 2 or 3 journals, hoping one of them gets accepted, and then you get 2 accepted or something like this. And these, I've seen all of it. I've seen the big one is plagiarism, because that's the easy one to see, because we have the authenticate to look at plagiarism. And the other ones, data fabrication, is harder. If somebody fabricates, how do you know they fabricated it or whether it's real? Yeah, you have these data points and all that kind of stuff, and they fabricated. So that's really, really hard to figure out. But that is really big. To me, if somebody does that, it should go even to their university, where they get really flagged. Like some people can even lose jobs for doing that kind of stuff. This, I'm not, I mean, like copying like a paragraph or something, it's fine. Omitting authors, I've dealt with that example. I had one guy in France. He did not include his student, and his student was the one who did all the work. And then they didn't get along. The student left. They didn't finish their degree. 10 years later, he was looking at papers and was like, oh, this is my work. It was published, but I was never included. And he should have been maybe first author, because he started writing it, and then he contacted Elsevier, and the other guy was reprimanded, and because he should have included. I don't know what happened like exactly, but anyways. Now, where ethical issues matter is that if something you did is wrong, it will never leave. They don't take, like if you submitted a paper and got accepted, and somebody figures out you cheated, even if it's 5 years later, it remains published with this big thing says retracted for plagiarism or for whatever. And that's not good for your reputation, of course. So that's good. Why it's really important to know that you cannot do that. Now, what I found sometimes, like sometimes a person that comes like to our university from somewhere, I'm like, oh, I can just copy my English, and I'm like, no, you can't do that. So we have to train our students to understand what are the limits of what's feasible and what's not feasible. Okay. Next, this is the part that I don't know exactly stuff because I'm new to this. So AI is an umbrella term for learning algorithms that make predictions that can produce new content based on a given input. So can we use it or can we not use it? This is the new stuff that I just got. So why should we think about AI in the context of scientific writing and publishing? This surprised me, to be honest with you. I just got this. Researchers recognize the potential of AI, and if they're not already using them, most expect to use it in the next 2 to 5 years. 96% of researchers have heard of AI. What did the other 4% not hear about it? What's going on? So these 4%, or anyways, 31% use it for work. 95% think it will help accelerate discovery. This is, how to say, polls that were made. That's what we get. So many of us, I don't know if we can use it, we cannot use it, and how can we use AI, etc. So the big concern, and everybody is aware of that, researchers are also aware, they believe it could be used for misinformation. And that is true. Next, what are the key concerns? I'm going to show you 2 slides of key concerns and then 1 slide of the good stuff for using AI. Key concerns are inaccurate information and unreliable sources. AI is not trained yet for scientific research, can also mislead us with information, and can give you incorrect, like if something is online that's not real, that somebody is putting up there, it also will pick it up and tells you, okay, do this, right? This is just an example. I was like, I was following, because I was born, Nacia in Argelia, on Norway coast and all that. I was looking at World Cup. Like the next day after Morocco made it, I said to AI, did Morocco, what are the countries that made it to World Cup? It did not have Morocco in there. And I said, no, Morocco made it. And then, so it went and we checked and they're, oh yeah, you're right. You know, so it doesn't tell you, and this is just for soccer, like for football, you know. Anyways, ethical concerns and biases also. So the models often lack transparency. 3, environmental impact. AI uses a lot of energy. It uses like these fancy computers to do these calculations. They're building them all over the world, and they use so much energy. So if we can do our own research without it, I think we need it. But it's also, we have to think about what's, you know, having a minimum environmental impact. So dated information, it doesn't know what, like whether something is brand new or not. So when AI tools are used, which the data set is outdated, it does not provide current news or information. It's not trained with scientific data. And sometimes, and I see this all the time, homogenization of content. For example, if you have used ChatGPT, every time you ask it to do something, it goes and writes it like this, and then in how to say, doesn't have in parentheses. It always does, what are they called? Dashes, yes. So it uses dashes, and then it always puts everything in bullet form, and it does it in the exact same way. So in science too, it's going to be homogenized to do the same thing the same way, because that's what it thinks the most efficient way. You know what I'm saying? And it's going to repeat doing that all the time. Having said that, new benefits also arise. It saves us time and effort. Sometimes I'm like, oh, instead of going and looking for papers, can you tell me what papers I should put in my introduction for my paper? Who has worked on this? Can you do an exhaustive search? And it does it so fast. It would have taken me maybe 10 days or 2 weeks to find all these papers, and it finds them in like in less than a minute. So that's really helpful, and that's a good thing for science, because then we're more efficient. 2, it can also help improve language. Many people, English was my 4th language, okay? And so it helped, like many scientists are not English speakers. For example, if you publish in an English language, this helps you. And even American students, because I work in the US, they don't write well. So it's like having something, unless I had to, or I do it, improve on their papers the way they're written, you know, so. It also identifies novel research topics. Sometimes I go and ask, hey, what can I do with these high temperature ceramics? You know, like, and then it comes up with some things. And sometimes I'm like, That's a great idea. Sometimes it really pushes me to the good stuff, and sometimes not really. And then promote research. You can also create promotional copy. I mean, I don't do this and support education. Okay, I don't know. I've never done question banks and quizzes. Anyways, so I think could make science more accessible, assist with manuscript checking and screening, whether it can also do a check whether there is any plagiarizing. So it does that as well. It helps us find reviewers. It helps us match manuscripts to a journal, etc. Now, this is now the new policy of Elsevier. Like I said, I just got this week. We have a new manager. I asked her to send me this information. Authors are allowed to use, you can use AI to summarize, analyze data, discover trend topics, or deepen your knowledge. You can do that. You can use it for writing only for improving readability. So if something is not well written, if it improves the way it's written in like only readability, that's okay. Some other journals don't even allow that. But Elsevier, this is the new Elsevier policy. Okay. But you need to apply human oversight. And and you need to disclose that you've used it. Disclose it. Not as an author, but you need to disclose it. Now this one for editors and reviewers. I've seen some editors or reviewers go, upload the paper and say, can you write me a review? And it sends you, it has a review. And people are doing that. Even as an editor, to be honest with you, I tried it a couple of times just to see how it does things. When I get the reject, but where I'm not, this is a new thing, I cannot use it, right? So do not upload the manuscript into an AI tool. This may violate confidentiality also, because whatever you upload to that AI, now everybody can have that information, okay? 2, do not upload peer review report or editorial decision letters. They may contain confidential information. And it cannot be used to assist in the review process or in evaluating and making a decision on any manuscript. So we're not allowed to do that. And I think that's a good thing. Figures and images, no. Also, you cannot generate a figure with AI and publish it, even if it's like describing your equipment or something, like my talk this morning, because it was a talk, I would have did it, but I would not publish that figure. Also, exception, which most of us don't do, is where the use of AI tools is part of the research design and research methods. So that's part of your research as well. Okay, so somebody's doing papers on AI stuff, and then want to show how how it generates this and how it generates that, then you can, but otherwise you can't. So all figures, you have to make your figures yourselves. Okay, so in summary, our or AI policies with Elsevier for now are responsible use, protect authors' rights, adaptability and alignment, which means still monitoring. This is still new. Things might change in 2-5 years, and receive feedback for and answering questions. So if there is any like we're still getting a lot of feedback, or Elsevier is getting a lot of feedback from the community of what they think on how things are working out, and then maybe adjusting later. I don't know. Because these things that I mentioned earlier, these are new. They didn't have them a year ago. And then in summary, to become an author of a reputable journal, you need to create novel and interesting content, decide on the type of paper you want to write, find out what are the requirements and suggestions from institute, universities, or funding agencies, collect the references of the paper and look for likely links, check the scope of your journals, finalize the paper and submit it. Don't do anything unethical, and enjoy the process of writing your paper. Do not worry too much about the outcome. Okay. All right. Thank you so much for your attention. Senor Steve. Okay. Let me say it a little different. Computing is not the same thing in a sense. Okay. Let's say when I was a student who did C, I wrote the Fresnel equations to do multi-layers reflections. Once my software is correct, it will always be correct. It cannot be wrong when it was C++, because it's using the right equations. It has the computer is like the program is correct. This is not. This is still has a lot of subjectivity to it because you're asking a machine to make subjective decisions. But in science, okay, in science, but for like a big data, you mean? Yeah. That's what I was gonna say. Okay, so I was gonna go play both like devil's advocate. I mean, I was gonna play both sides. So what I was gonna say is, having said that, it has a better chance of getting closer to the reality because if you say, hey, only look in scientific papers, for example, if you're in medical field and I'm like, oh, can you look in papers? What do you think about this vaccine? Then it goes to papers. It doesn't look at what the crazy person is saying. You know what I'm saying? Yeah. So as long as you can verify that, then it could be useful. Like it could be, it should be very useful, right? So yes. And modeling also with the computers, you get MD, for example. Molecular dynamics is a different story because then you're trying to model how a material behaves at a certain temperature or something like this. But maybe that force field is not correct, or so even in computing, it's the same thing. No, I agree. Yeah. Mhm. Yes. Yes. Yeah, but we also know the person that writes your computer model, you have control over it. AI, I don't have control of it. Or the computer model, if I don't use the force field that's right, I know it's like, but I'm gonna have an error of 5% because my force field is not correct. But yes, yeah, okay. But you go and ask things that are, let's say, political, it will never be right because there's half on one side, half on the other side. And they're putting a lot of rubbish on both sides, and then yeah. Uh-huh. Yeah. Una otra pregunta de una otra persona en español, por favor, señor Pancho. Okay. I don't have a blacklist. One time, our editor-in-chief brought that up, and he's like, "There's one person, he publishes with us all the time. He has published with us 25 times. He never reviewed a single time." And he's like, is that you? Oh, maybe he was talking about you. But we can't do that. Regardless, that's you can't blacklist people. Just like when people volunteer. Some people volunteer more than others, and you can say, well, you know, we don't have a blacklist. No, I've never seen a blacklist. I know if I see the names multiple times, and we know, but it's not blacklisted. I know if I put your name on the system, I know you were asked 100 times and you were reviewed once or twice. You know what I'm saying? That we have that data. We have that data, how many you have reviewed and how many times you've been asked. That we have. No, there's no unacceptable. Even if somebody never reviews, there is nothing against that person. I've never seen that. Seriously. Yeah. So don't worry. Yes. We play, I mean, we all play tricks. I mean, that's not a trick, but yeah, no, it's not a trick, this one. Even me, like, to be honest with you, my student is presenting 3 talks. It's more or less very similar at 3 different conferences. I'm like, just change the title. Don't change the abstract. It's fine. It's 3 different places, but on your resume, it looks nicer if you have 3 different titles. That's true. Right. No otra pregunta. Muchas gracias para todos por venir y gracias.